Okay, hello everybody. We are back for the 5th days of the Grayscale School. So here we will do some magic with Python. And at the end of the day, we will do also some magic with the operating system, because of course, the operating system tries to trick you as much as possible. So here we'll have Jean-Marc to present the first part of the lecture, and then Alice will also present other optimized stuff in Python. So Jean-Marc, it's up to you.
Thank you, Pierre. Hello, everybody. I'm Jean-Marc Collet. I work in Sorbonne University in Paris. So today we start Python with profiler tools. After we will see Numpy, Numba, and this afternoon we will see JAX. And Sébastien Valla present pyramid method for Python. So I start the profiler review with a proposition of optimization roadmap. So to start optimization, when you have a reliable and tested version of your processing, use a real case use case. Establish a benchmark result to verify that your optimization don't degrade the quality of processing. Identify the task that take more time and optimize it. It is sometimes practical to isolate the critical part of the code to optimize more easily without redoing all the processing. And when this part of code seems significantly optimized for you, redo the global profiler. Optimization is an iterative process. So to successfully optimize code, CPU and memory profiling tools are indispensable. They reveal bottleneck in execution time and memory usage, enabling effective and measurable improvements. So the first profiler is a C-profile. C-profile is a profiler built into the Python language, available without installation. It's launched as an option to the Python interpreter. So Python -m C-profile -s cunTime and the name of your script. In return, we will receive the list of the function in my script, sorted by cumulative CPU usage time. C-profile is very precise, reading the measurement time, but significantly slows down execution by a factor of nearly 10. Another profiler is PySpy. PySpy is a cyclic profiler for a Python program. PySpy is much faster and remain accurate enough to identify bottleneck. In fact, the sampling rate remain configurable with error option for more precise result. So here you have the link to the project. PySpy has a free mode of operating. For profiling, we use the record mode, which allows you to generate a result file. And by choosing the speedscope format, you can visualize it interactively on the speedscope website with nice interactive interface. So here you have the complete command to run your code with PySpy for speedscope. So record mode, output in a JSON format. Here's to use a speed scope. Here it's a rate sampling, and at the end the script. So you download this file in the website here. Oops. Yeah. You choose your JSON file, and you have a view like this. You have different view. There are 3 view modes, and you can see here time order, left TV, and sandwich. And sandwich mode is the most interesting. It's the equivalent of the C profile cumulative time. Is here, see this column. Here you have the name of each function and the time associated. You can sort it by name or by cumulative time. And the view give also the calling and the called function, hence the name of sandwich. So here you have the function start with keyword. You can see this function. Here it's a caller function, and down it's a called function. Now, at function level, you have a light way to time the duration of a function is to use the timeit module. Timeit function associates and defines the function to estimate as an anonymous function with lambda. The number of iterations is configurable, and the return value is total duration. So here you have your function, and to time it, you need to use this syntax with lambda. And you can configure the number of iterations. So that is inside Python. So you must instrument your code. If you use IPython, you have the magic command timeint with syntax more simple. And they give also almost the same result. So tips, in practice, the first step is to identify the slowest function using the profiler, and then try to optimize it with timeeit to measure its performance. Another kind of profiler is a memory profiler. So the basic tool is tracemalloc. Tracemalloc in a standard Python library. It provides the following information: track back when an object was allocated, statistic on allocated memory blocks by file name and par peer line number, total size, number, and average size of allocated memory block. So here you have an example to return the top 10 of memory allocation by line. So you must instrument your code with import tracemalloc. Declare start session with struct-malloc, and you have the statistic with this line. And at the end of the processing, you can print the result like this. So the return. Oops. The return object is topstat, and in simple loop on topstat give this information. There are another sample tool for memory profiling. It's a memory profiler. It's a Python module to monitoring memory consumption of a process, as well as line-by-line analysis and memory consumption for Python programs. Here you have an example. So you must import a memory profiler module and use a decorator profile to profile the function you want to analyze. After this, you launch your script with option memory profiler, and the return your code with memory usage line by line. So you can see here you have free memory with del, so the value is negative. For this tool, you have also an IPython integration. So after installing this module, if you use IPython, you can use a magic command mprun to get memory consumption line by line like this, or memint to get the global memory consumption. And at least you have a malt. I think you also see malt this week. Malt is a high-performance memory profiler that provides numerous metrics via a web page with code annotation, designed for scientific computing with compiled language such as C, C++, Fortran, and Rust. It's now also available for Python. To use Malt, you need to launch the script with Malt Python, and then open the result file with Malt web view. And here you have an example of the view, Malt view for Python with code annotation. This afternoon, Sébastien will analyze Grace Code Python code with this tool. So the presentation of Profiler is finished. Do you have a question? No? Non, je ne sais pas ouvert. Okay. So we will switch on Numpy course. So Numpy. Numpy is an essential Python library for scientific computing. It's made of more than 500 functions for fast operating on array, such as Fourier transform, linear algebra, random generator, math function, and so on. Numpy is mainly written in C and C++ and use a BLAS and LAPP library, which ensure SEMD vectorization. If you use it correctly, you can greatly improve your performance compared to native Python code. We start with a review of structure available with Numpy. There are three structures. ND array, matrix or vector, and structured array. ND array have the same type. All elements have the same type. You have the memory element for SEMD, and ND array can represent a signal, time series, image, scalar field, spectrum, and so on. Matrix is in fact a 1D or 2D ND array, and you have you can apply the linear function for linear algebra. And for a structured array, it's a set of ND array with a column name. Donc you have heterogeneous type like data frame in Panda or Qtable of AstroPy. And they represent signal, metadata, and parameters in the same structure. So as we see, ND array is a central object of the Numpy library. So ND array is for n-dimensional array. The main attribute is shape, return a tuple. Return a tuple with the number of elements in each dimension, like 10, 200, 300 for 3D array. All elements have the same type, defined by attribute dtype. Numpy defines the own types, like float 22, int 16, and so on. And you have access to the occupation of the array in memory with n bytes. There are other attributes, but I present the main, the essential attribute. And for method, the principal method is reshape. You can redefine the number of elements in each dimension. But in the NumPy vocabulary, you use axis instead of dimension. You can do conversion to another type with as type, and you can copy the array with copy method. So some example of ND array creation. You can create an array with a list, Python list. You have some function to a specific array, like all value is zeros with NP zeros. So the argument here is the shape of the array. So 2 lines, 3 columns, line columns. Another one is 1, so when the all element is equal to 1. You have also an empty, so you don't initialize the memory, so you can find anything. Like you see here, there are strange value, almost the same, I think, yes. And also you can copy the shape on our array with function family LAPP. So you have empty LAPP function, 0 LAPP function, 1 LAPP function, where the argument is another array, and it keeps the shape of the array in parameters to initialize the return array with 1, 0, whatever. It's a very practical function to define an array. There are another in this link documentation. So you can consult it. Some reminder of slicing with Numpy. In fact, Numpy uses the same slicing convention as Python. So the first index is 0. So you can define an interval. So remember when with Python you write the lax index. The lax index is excluded. It's equivalent to the mathematical notation like this: open and closed. They support negative index, where -1 is the last value of the array. To define the two first elements, it's 2.2, and to define the two last elements, it's -2, 2 points. To have whole elements, it's 2 points. Now we will about the broadcasting. Broadcasting is a central concept of Numpy library. It's allowing you to avoid writing a Python loops. The emblematic example is the multiplication of array by a scalar. So here you define a simple array, and if you multiply the array A by B, all elements of the array are multiplied by B, like if you write a loop. So the syntax is clear. It's also very fast, because the loop is performed outside of Python. So here you have a representation of the broadcasting. Here you have your array, and the scalar B, in fact, is stretched to have the same size of the input array. And after you can apply multiplication element by element. So this concept can be extended for the higher dimension number. an example with a one-dimension array and two-dimension array. If the number of the 1D array elements match with the number of 2D array. So here you can add for each row of array a vector if the dimension of the vector has the same number of columns of the array. So as the same manner for the scalar, the vector is stretched along the row to have the same number of elements of the array, and after you can apply the addition by term by term, element by element. So here you have the constraint to use broadcasting. So the first is the dimension alignment. Numpy compares the dimension of two arrays starting to the right. And you have constraint of dimension compatibility. If the dimensions are equal, no problem. If one of the dimension is 1, it is stretched to match two other, like in this case. Otherwise, Numpy has an error. So an example of broadcasting where use is not obvious. So it's a multiplication of array of an image by a calibration of scalar, but specific to each image. So it's a vector with the same number of image. The choice of the shape for array image is 10 image with 200 row and 300 column. And the calibration vectors is n, like the number of image. So for this example, I can initialize my array image with a random function and apply the reshape function. You can also define the shape directly in a random function is possible. So you define the image like this, and for the coefficient vector, it's a vector with 10 value. And if I want to multiply coef by image, like this, I have this message error. So we will try to understand why is the error up here. Okay. So the message error is operand could not be broadcast together with shape 10 on 10, 200, 300. So like a rule say, Numpy compares the dimension like this, start to the right. So he compares 300 with 10. So the error is here. So what should we do? There are three solutions. Return to the case scalar multiply array with Python loops. And it's required to modify the shape of array. Solution 2 modifies the shape of the image to put 10 to the right. So in fact, 10 is here. You can change the shape to put the 10 at the same rank than vector. Or you can move 10 of the vector to the left by introducing a new dimension. So we start with the solution 2. We will modify the dimension of the array image. So we have a family function to modify the dimension, transpose, just reverse the order. So transpose for the array, put 10 at the right and 200 at left. You can only swap 2 axes. Or you can move axes, but in fact, you insert the dimension at rank you want, and the function pushes the other axis to left. Donc for an example with move axis and array, donc you put the dimension, the axis 0 to the 2, donc 10 to here, and the return function is the new shape is this one. Okay. In fact, if you modify the shape of the array to multiply with the coefficient, and if you don't want to modify, you must apply two times the modification to return to the original shape. So the solution 2 have 2 swap axes, one to perform the broadcasting, and another one to return to the original shape. Okay. We time it this function, so now there are no errors. You have the result here. Now we will see the solution 3. We will introduce a new dimension. So we start with a vector, so 1D array. In fact, 1D array, you can see it like a 2D array, but with only one row. It's a point of view. You don't introduce new data. And with Numpy, it's possible with the notation new axis, which increase ND array by 1 dimension with a single element. You have also the function does the same things, is expand dims. So we start with a vector. So the shape is 3. And with this notation, we insert a new dimension in front of the vector. And now the shape is 1, 3. So now you can write the solution 3 with a new axis. So from shape 10, we want to go to shape 10, 1, 1 we need to apply 2 times new axis at right. And you have a shortcut to do that. Instead to use Numpy and new axis, you can use a keyword none. So the solution tree with notation is here. So coefficient, you take all elements of the vector and you put 2 dimensions at right. You time it this function, so there are no error, and the result is almost the same as this solution. In fact, this solution with additional dimension is the solution shows the most of the time because the syntax is clear and short. So now we have 2 versions of the multiplication array coefficient vector. We will compare the result. So here you can write the naive solution with Python loops, and here it's a multiplication by a scalar. So you obtain this time, and to check the result between solutions, we will use a Numpy function called allClose. This function compares term by term all elements of the array and return a Boolean. So we compute the free solution with the result of the free solution. After you check if you find the same result with allClose. So it's okay. So as we see, the version with broadcasting is 2 times faster than Python loops. You see 200 microseconds, and here around 450 microseconds. So the speed up is a factor 2. Broadcasting limitation. You can find this warning in a Numpy documentation about memory consumption of the broadcasting. There are some cases where broadcasting use a lot of memory, and in this case, the documentation recommends to write a Python loops. And maybe the best way is not to write a Python loops, it's to use number library to do that. We will see it this morning. Oui.
There are a few questions on the Discord for Jean-Marc. The first one is, under what circumstance would one use numpy.empty?
Why you want to use empty?
Numpy.empty.
because there are no initializations, so the function is more efficient to return an array if you don't have if you don't need to have an initialization.
And a question on broadcasting. Does broadcasting an array take more space in the memory, or is it like using pointers to the same memory place?
So effectively, when you perform the broadcasting, you can have some memory issues like the documentation said. So at the stage of the multiplication or operating, when the broadcasting use, you have memory consumption. But after, no.
Well, if you have more questions, ask them in the Discord, and then Jean-Marc will answer them at the end of this notebook.
Okay. So in case where broadcasting use a lot of memory, you can use a Numpy library. We will see it after. And also keep in mind in your benchmark, do it with a realistic data size to avoid the scaling issue. If you test your program on with a small size of data, this kind of problem appear when you increase the size of your data. Now we will see another part of the Python of Numpy performance is processing in place. So in-place processing perform over the data in the array, and result is stored in the same array without memory allocation. With in-place processing, you save time by not requesting a memory allocation, and it's an important concept of the optimization. So some reminder, when you write b equal a in Python, b is in fact a reference to a without copy. It's a Python feature. When you use a Numpy array, so a is a Numpy array, and if you define this variable line as the first line, so the first line, and you keep the first line with all elements with 2 points. The variable line, it's an example of view of ND array. Numpy don't create a new variable with space allocation, and it's just a pointer of an array. So it's a view. It's a concept to know to use in-place processing. And in fact, with a recent Numpy version, the function like transpose, new axis, swap axis, return a view of array and not a copy. So you can do a broadcasting with this view if necessary. We have also the classic in-place arithmetic annotation, plus equal, minus equal, and so on. And for most element-wise function, you have a parameter out to define the variable the variable where the result is stored. If you define the output with the same variable as the input, you have the in-place computation. So all functions with element-wise function have this parameter out. So the first version we wrote of the multiplication of image with coefficient create a copy. And now we write a version without copy. So I wrote it directly. So with a naive loop, you use the classical in-place arithmetic to put the result directly in the image. So it's in-place implementation. As we see, we don't have a written image like this one. Here you have the copy is explicit. I don't merge the input with the output. In this one solution, we swap. So I start to create a view of the array with snap axis. So I have an image view without a memory allocation. And I multiply this view by coef. And the result is, in fact, in a variable image. And for new axis approach, it's very short. It's you use the in-place arithmetic in-place operator with a new dimension to satisfy the broadcasting. So if you return to the previous implementation, so here when you write return, you create a new copy of the array. This operation creates a new copy. So like for previous solution, we check if the results are okay with all close function is true. So the important things for the in-place processing, you don't have a written object. So the input object is also the output. Some tricky thing with to time it this kind of function. In fact, you do this this operation like a suite, and the result can diverge quickly. So to avoid this, you reduce the number of iterations. And now you can compare the in-place version with duplicated memory. So now for swap axis we have 100 microseconds, and before we have 200. So we win times 25%, I think. So with in-place implementation, you improve the performance of the operation. Now we will see another kind of implicit loop with the reduction function. So the reduction function is an operation that summarizes several values into one, like sum, average, max. Numpy implements a mechanism to iterate through element to avoid writing a loop with the axis parameters. So axis n indicates that the reduction loops is along the axis n. The result in the array, the return in the array, the size along this axis is 1. It's a reduction. By default, the axis is squeezed. So you return an array without this axis. But you can keep it with this parameter, keep dim true, to keep the original shape of the array. So here we have an example. We define 2D array, and you want the sum of A on axis E. So in fact, you reduce the column. So the result is for line. So sum say 1, 2, 3, 3, 4, 5, 12. If you call this function with the parameter keep dim, you keep the shape of the array with 2 dimensions. Another area where Numpy provides a functionality to avoid writing Python loops, it's a selection element from an array to make another array. So we have two ways to do that. You have the fancy indenting. You can put an index array or a list between a bracket of array. So AA is a 2D array, and you can select some element of the VS array with this syntax. It's a fancy indexing. For example, you can collect the maximum of each line of a 2D array. So 2, it's line 1, column 2, and for line 2, it's line 1, column 2. So here you have the maximum of each row. But for larger array, it's not practical. You have a function called take along axis to select some element of the array. And typically, this function is compatible with the output of the arg function family, like argmax. So if you want to keep to have the maximum on each row for large vector, you call argmax for the axis you want with the parameter keep dims. And after, to collect the max value, so here you have the index of the max value. Here you have the return of max value. So you call take along axis the name of the array and the index where the maximum is R. And you see you have the same result. So conclusion, we have seen the two important concepts of Numpy to obtain good performance. Implicit loop with broadcasting. You have a reduction function with a parameter axis and selection function with axis et puis this function take along axis. The other concept is the in-place processing. Where you use view of array, you can use the parameters out of the element-wise function, and also the classical operator in place add equal. Okay, so the introduction of Numpy is finished. You have a question? After I have some exercise.
On the Discord, there is a discussion on numpy.einsum. Einsum. They say it's faster than, it's easier to use than numpy.swapaxis. Do you know it? Do you use it? Einsum.
Ah, non, comment ça s'écrit?
E-I-N-S-U-M.
Sorry, I don't know.
And another question is the column operator 2 points, 2 points, some alias of take along axis?
Maybe I will answer to the question during
Yes.
the exercise.
Okay, yeah.
So I propose you some exercise. So we have access to the course. So in fact, so if you want to do some exercise, you can use the Grayscott Python package. To install the environment. So, I don't know how you work. But if you are on local with your laptop, you can load this package and just run pixie run Jupyter Lab to have the course, the exercise, and the Go environment to run it. So the link is so the first exercise is slicing exercise. We'll create an array with shape 6, 4. And you must return the inner sub 2D array from tab array. And you must replace this character by the good one to obtain the sub array. So you must select this one and this one. If you have some problem to install the package, I can help you and list too. It's okay, no problem.
Pour pouvoir compiler les cellules, est-ce que j'ai besoin d'utiliser mon environnement personnel ou bien j'utilise PC? Parce que j'ai créé un environnement et PC.
Ouais.
J'utilise juste PC
Ouais.
run Jupyter Library Compute automatiquement.
Ouais, il faut sélectionner l'environnement
L'environnement.
Pixie du package.
D'accord.
Tu veux, on fait ensemble?
Ouais.
Ouais, c'est là.
Mais
Python environnement.
mais il n'y a que l'environnement virtuel et je ne sais pas s'il faut créer.
Alors, tu peux aller en ligne de commande.
Bien sûr.
Peut-être faire un Pixie install avant pour le compiler. So someone can give the solution? So élément 9 is line 2, colon 1, and 14, it's line 3. And 4. Remember the index at the right is not included. Ah oui.
Il y avait une analyse. C'est juste ou pas?
Euh,
2, 4, 1, 3.
ok. Ok, c'est ça. So the good answer is 2, 4, 1, 3. Okay. So 2, 4 is to select this line, and 1, 3 it's to select this column. Second exercise is broadcasting, an array 2D and 1D, and calculation in place. So we define a 2D array A and a vector V, and you want to add the vector to each line of the array. So you have in the same case as here. You have the same in the same case. And here you have the loop version with Python and with copy memory. So try to find the code to process in place and use the broadcasting. So to do that, you can modify the shape of A or modify the shape of V. You must check if you find the same result as the loop version, the Python version. You can see you can measure the speed up. Voilà. So to use the broadcast is it's very easy. You add a dimension. You add a dimension to V, and you add with A. So we find the same result. So here you have a duplication copy. So now to have a without copy. With in-place implementation. You use the in-place classical syntax, like this one. So before call it, you must copy it because the in-place version modify it to perform the comparison. A copy and check if the result is the same. No, it's no, sorry. So result in place. with a result with the loop.
Yeah, you forgot to put a copy on the line, on the broadcast in place line.
Sorry?
Forgot to put a copy on the broadcast in place line. Yes, instead of a.
Oui.
Yes, actually, you should copy a before doing the first one. If you, the a copy should be done before
Oui.
the first in place. I don't know actually.
There are no output.
Okay, my bad.
Okay. So we have the in-place implementation. Okay. Last another exercise is to perform this operation sinus AX to B in place without any copy duplication. Here the A, B are scalar. So you keep the result in X variable. Yes, right. Time. So to write in place, you use a classical operator in place. So you start to multiply x with a. After you add b. And at last, you use the parameter out of CNRS function to put the output in input. Right, some issue with timing. So sorry, the time is finished. I will give you the good solution after the coffee break. Okay, thank you. We will see you in 20 minutes, 30 minutes for Numpy with Alice 4. Thank you.
Okay, so we are back to the break. So Jean-Marc, I have a few things also to discuss with you, and then we will move on with Alice with the new magic. So Jean-Marc, it's up to you.
Thanks, Pierre. So I fixed my issue with time it. I just forgot the parameter for a repeat. So I can compare now the version with the in-place version and copy version. So as you can see, with copy we have 45 milliseconds, and the in-place version only 20. So the speed up is it's a factor 2. So now I will Alice start with Python implementations of the Gray-Scott reaction.
Thank you, Jean-Marc. So we are going to switch to the practical part, where we have to implement the Gray-Scott reaction in Python, and then we have to optimize it. So for this, it's better to use the notebooks, as Jean-Marc showed you. So if you have any problems with opening them or running them, just let me know, because or for the next this hour and then this afternoon, we're going to use the notebooks extensively. So the part we're doing now is the third notebook in the tutorial directory. You also have a solutions directory in which you will have the solutions of the notebooks. Okay, so we're going to do the 3 and 4 today, and maybe the 6th one, we'll see. Okay, so our goal now is to implement the Gray-Scott reaction in Python. So Gray-Scott reaction, by now you should know what this is, but let's just get on the same page together. So with Python, we're going to want to use the computing libraries to speed up our code, because as you may know, Python is used most of the time as an interpreted language. And so we do not compile it to machine code like C, Fortran, or C++. And instead, the source code is compiled into bytecode, which is an intermediate format. And then it will be read and executed line by line by the interpreter. So usually Python code is slower than fully compiled code, but it's also more flexible and easier to use, and this is why we all know Python. So we want to use computing libraries in Python because they are written in C and they are compiled. So Numpy, math, etc., they are all written in C and compiled. And the only slowdown in execution is when we call them through the Python code. So an easy way to have a fast Python code is to spend most of the computing time using these optimized libraries. We can also compile some subsets of the Python language with, for example, Python or Numba to speed up the Python code. This afternoon, we're going to see Numba and how to use it in our case. So let's take into consideration the Gray-Scott reaction. So as you may know, it's a diffusion reaction. You have 3 species. And so you add U at a given feed rate. V uses U to grow and is removed and transformed to P at a given kill rate. Okay, so these are the parameters we will have in our computation. U and V are going to have the arrays on which we will compute, which represent the concentration of U and V species. I think Pierre explained it already on Monday. We use here a discretization of the Gray-Scott reaction that represents, so we use a stencil to represent the Laplacian of U. We create 2D grids where we compute U and V at each cell. And the result will be a succession of images that describe the evolution of the concentration. So how do we discretize this reaction? We consider that the species diffuse to their neighborhood, and so we can represent the neighborhood in, for example, 3.3 grid. So here, for example, we consider with the von Neumann neighborhood that the species U will only diffuse to its 4 closest neighbors. So you have U at the middle, and it will only diffuse to the 4 closest neighbors. This is a stencil that maybe you know, but in the Gray-Scott reaction, we will consider that the U species will diffuse to the 8 closest neighbor. So the diagonal ones and the up, down, and left, right neighbors. So we use a Moore stencil. Okay, so maybe this is the one you saw in the previous classes. So we consider that our species will diffuse to the 8 closest neighbors. So this is the stencil that we're going to use, and we're going to use it to compare with the implementations that you already made in C++, for example. So the first step of this this tutorial is, well, first to import the libraries. So I suggest you to run the cells as I run them so that you can see if you have any problem. If you have any questions, ask them, because it's important that you manage to run this tutorial by yourself. So let's import the libraries. So we use Numpy, because in Python, if you don't use Numpy, you have a very, very slow code. So it's always better to use Numpy arrays instead of Python lists. So let's first define the stencil. So we use our Moore stencil, and we use float32 as our type for this whole implementation. So we have to be very careful to always specify it. Okay, so let's try that. So we defined our stencil. And now we're going to write, so you are going to write actually, the computation kernel. So to do this, you have to go all over the U array, so the array that represents the concentration of U, and you have to compute the Laplacian by applying this stencil, that is a discretization of the diffusion process. So you are going to use NumPy vectorization by broadcasting your computation over the whole U array at the same time. Well, in our implementation, we will cheat a little bit and use images of size a bit higher than the HD size, and then we're going to reduce them to the HD size so that our borders are not taken into account. So first step is define this Laplacian function that will apply the stencil to U, okay, to the U array. So you're going to take an array that will be the same size as U and also the same type, okay? So zeros like here in the NumPy function zeros like will define an array that is the same size as U and the same type as U, so float32, and it will fill it with zeros. We could have used also empty if we don't want to initialize it. So here you have to fill the body of the function using 2 loops, okay? You have to apply this Laplacian to the U array. I will give you maybe a few minutes to do that. And if you have some trouble understanding what to do, you can check the solution, but I advise you to try to do it. Normally, you should have already done it in the other classes, so you should know how to do it. So yeah, and then we'll see the solution together, okay? Did you all manage to install to run the first cells of the Jupyter Notebook? Yes, are there any questions? Okay, so try to fill this, this function here, and in 5 minutes we correct together, okay? it okay? Yes. Okay, cool. Here in this function, U is the 2D array. We're going to define it later, but this, just for this function, consider that it's a 2D arrays of the concentrations of U, and it's the size Hg plus 2. And the two loops that you're going to write here are loops over the stencil elements. And then you apply these stencil elements over the U array with the broadcasting. Ah, yes, cool. Okay. Did you manage to install? Ah, you just arrived. Okay. Okay. You have installation instructions in the Discord. Yes. Okay, let's check together the solutions. If you struggled a bit, writing these two loops is no big deal, because really it's not the fun part. You have to play with the indexes. It's a bit annoying. So we write two loops, one that will be on the rows of our stencil, and one that will be on the columns of our stencil, okay? So we take the last, the first, and then the last, the middle, and then the first. And we apply it to almost, I mean, the Laplacian, we're going to fill it at almost all the elements. We just leave the borders at 0. It's our little trick to not take into account the borders. And so this is what you have to write to do this computation, to apply this stencil over the U array to have the Laplacian. It's a bit cumbersome. If you didn't manage to write it, it's okay. It will not be the interesting part. So if you did not manage to write it, you can just copy paste the solution here. But that, yeah, so the principle here is that we are going to broadcast our computation over the U array. So we use this indexing here. We take the rows that are from this row to this row, and then the columns that are from this column to this column, and apply the stencil, okay? It's a bit cumbersome with the indexes, so don't worry too much about it. So now that you have your Laplacian computation, it's going to be a bit easier. So we are going to test this function. to see if it works. So to do that, you need a function that I already wrote, so you don't have to worry about it. It's the function that will initialize our arrays. So we have two arrays that represent the concentration of U and V. And we are going to, so there are of size hg plus 2 of type float 32, each one. And we are going to add a drop of the V species, I guess, in the U array. Is that it? Or maybe it's the other way around. Anyway, so yes, so U will define it as an array that is full of a species, and then we add a little bit of V at the middle. Yeah, I think that's it. So normally you have seen this function already in the C++ class. So this is just the initialization of the U and V arrays. And then we can use this function. So try to run this. Well, for me, wait. And then we're going to use this function here. And we're going to get U0 and V0, which are going to be our initial conditions. And then we apply our function Laplacian Numpy to, for example, the U0 array here. And we have to also pass the stencil as argument. OK, so try to run this cell. Normally, it should run. So I'm going to take my, yes, this one. OK, so let's try to run this. So we define the number of rows and the number of columns here. And yeah, you see with timeIt function that will, if you put %timeIt, it will time the cell here, the execution of this instruction here, and it will repeat the timing a few times to give you a good estimate. So here it's taken us 22 milliseconds to compute this Laplacian. This is because we use NumPy arrays. If we use Python arrays, Python lists, it would have taken forever. OK, so now let's write our main function, our function that will compute the Gray-Scott reaction. So I'm going back to the tutorial. You have the description of the function here, so what it takes into arguments and what it returns. And what you have to do is to fill the body here to apply the Gray-Scott reaction, so to propagate the U and V species in the U and V arrays and so in the loop over these steps. Okay, so the number of steps that you apply is going to be defined by these steps. OK, try to do this. So it's just the Gray-Scott reaction. So U equals, and then you have to write the reaction here. Try to do it, and then we correct in 5 minutes or so. OK. Do you have any questions on the first steps? No? Everyone managed to run the first steps? OK. Yana? OK. Ah, yes. So there are 2 questions on the Discord, I see. I get, yeah. So the question on the stencil rows, why do we use -1, 0, and 1? I think I used that to make it easier for the indexes in the body of the loop. Yes, because if you use 0, 1, 2, then you have to subtract. You have to subtract 1 every time in the body of the loop. I don't know if that makes sense, but it was for convenience. And why do we use a 9-element Moore stencil instead of the 5-element von Neumann stencil? It's just our convention. we consider that the species will diffuse to its 8 nearest neighbors. But we could have considered it diffuse to its 4 nearest neighbors. It's just the convention that we took for this, this Gray Scott school. And then we have a question. How does Numpy broadcasting avoid writing explicit loops? So in the, okay, I'm going to answer with the solution. So in this function, if we didn't use broadcasting, so if we didn't apply the stencil to an ensemble of rows and columns here, that we take it with these 2 points. If we didn't do that, we would have to have four loops. So 1 loop over the rows of the stencil, 1 loop over the columns, 1 loop over the rows of the U, and 1 loop over the columns of U. Okay, and this here we have only 2 loops because we do this broadcasting over the whole U array. I mean, not the whole, but the rows of the U array and then the columns of the U array. Okay. I think in the Numpy tutorial we're going to maybe unroll the loops. I guess because Numpy is good with 4 loops. Maybe we're going to see afterwards. But yeah, here we use the Numpy broadcasting, and it actually is a good way to use Numpy in Python, is to always use it when you can. Okay. Oops, I showed the solution. Okay, so try to do this Gray Scott steps function yourself. Is it okay? Did you try? No. No? What's going on? Okay. Okay, let me know if you want to join the Okay, so let's see together the solution. So we are going to implement our Gray-Scott reaction here. So as I said, the G steps is going to be the we're going to be doing our for loop on the G steps. So I think in most of the school is 32 steps that we're going to take. So to apply the Gray-Scott reaction, so, you can go back, I guess, to the, yeah, I think that's it. So the variation of the concentrations with respect to time is going to be given by this. So you got R, which is the kill rate. You got the Laplacian of U here. And you have to do this computation, U times V square. And you're going to add the feed rate times 1 minus U. So this is for the U array, and for the V array, you're going to do the same thing, just a bit different here and here, okay? So yes, so U and V square, we're going to use it in both computations, so we can compute it one time and then reuse it for U and for V. So let's check. Okay, so we compute UVV, which is a U times V square. We update U, so here du must be the diffusion rate. And then we apply the Laplacian, and then we have this feed rate, yes, here, that is f, that is an argument of your function. And then for v is the same, but you just have to change some signs here. Okay, and so this computation, you're going to do it d steps times, and this will give you the variation of the concentrations with respect to time. Okay, so now let's include this function in a loop over the number of images we want to create, because this, we're going to create one image, and then if we want to create like 1,000 images, we're going to do this again 1,000 times. One problem we have here on this implementation is that we need to be careful of our RAM when we will save the results, because if we gather all the images we want to produce in a big array and then we want to save it, it might exceed our RAM because it's HD images. If we do like 1,000 of them, it might be a bit big. So we're going to create chunks of images to be saved one after the other, depending on the size of our RAM. So we're going to adjust the chunk size later. Okay, we also need one function to reset the borders between two iterations, two images rather. It's just some trick we made here to not take into account the borders of our images. So this is a function you can just execute. You don't have to write it. We set the borders of our two arrays to 0. Okay, and we do it between each image computation. So our function, we're going to call it simulate images chunk. Yes, I'm in a tutorial. And then this function will do the Gray-Scott d steps function for every image we want to create. Okay. So you have to fill the body of the function. We are going to gather our images in this array here. So it's of size k images. K images is going to be the number of images we want to compute in this chunk. So maybe like 80, 100. We will define it later. The size is going to be HD images. And then, be careful that the type is always float 32. And if we don't put this here, then Numpy will take by default float 64. And then we're going to have a much bigger array than we need. Okay, so fill the body of the function. And in the end, you save the images in the images array. And you remove the borders. Because U and V are of size HD plus 2. and you just want HD images. Okay, you remove the borders, and then you return images. Okay, try to fill this function yourself. Yeah, I guess it's yes, it's the last big function that you have to write yourself, and then we correct in 5 minutes. Do you have any questions on this? No? Okay. Yes, I think someone said it on the Discord. I think there is a confusion here. The feed rate is FR and the kill rate is KR, and RU and RV are diffusion coefficients. Okay, this is a mistake here. It's KU, no, FU and KR. Thank you for telling me. Okay, let's check together this simulate images chunk function. So we have our images array. For each image in this array, we're going to apply our Griscott dsteps function that is going to do the Griscott reaction dsteps times. We're going to reset the borders between each image. And we're going to fill our images array with, here we take V, but we could have taken U. It's the kind of the opposite image. And we just take the V array without its borders. And this is our first image. And then we do this K images times. Okay? And so now we're going to use this function in our bigger function that is going to do all the I/O processing, which is called simulate and save chunked. So we're going to simulate the reaction, save the results in an HDF5 file. Yeah, and then this is where we're going to use the chunks. So instead of doing everything, filling our array one time, we're going to do several times for chunks of images. This is a function that is already written. You don't have to write it because it's a bit annoying. Yes. So yeah, this is the main function that you're going to use if you want to do the whole computation, if you want to produce your images. We can also define two helper functions that you don't have to write either, that are going to plot the images from the HDF5 file, so that we can check that we made the right computation, that our results are good. And then we also have a function to create the video. So at the end, you're going to have an HDF5 file, which is very big, which contains all the results of the Grayscale reaction. And then you're going to make the video from this. So for example, it will contain 1,000 images, and you're going to make your video from those 1,000 images. And then if you want, you can plot some images from the HDF5 file to see if your results are good instead of making the whole video. Okay, so these are two functions that you don't have to write. Now let's use everything that we made. So let's define the parameters we will need for the rest of the class. So the size of the images, so HD images, the number of images that we want to produce in our video. So for the moment, we don't have a very optimized code. It's not optimized at all. So let's keep the number of images low so that it doesn't take too much to compute. The number of steps that we are going to apply the Grayscale reaction between each image. So here we put 10, but in the real the other implementations, it should be 32. But for now, we're in Python. It's not optimized. Let's keep 10. For our step in time, we just choose 1 second, for example. The diffusion coefficients, you define them here. The kill and feed rates, you define them here. And now, what you're going to do is, so first you initialize your arrays with the function that we defined previously. You can plot one array to see the initial concentrations. You give a path to the in which you're going to save your HDF5 file. And so what you have to do is you have to fill here, use all the functions that we defined previously to compute the Grayscale reaction, to save the images in your HDF5, and you can time also the execution of all this, and you can also make a video of all the images that we save in our HDF5 file. Okay, so try to do this. Use the functions. So here, so here you can just make the HDF5 file, and then here you can actually plot some images and make the video from the data you have in the HDF5. Okay, so try to call these functions yourself to get accustomed with our implementation, and then we will see how to replace some function with SciPy, and then we will tackle Numpy. Okay? So I'll leave you 5 minutes to do this, and then we check the solution. All right, so let's use our functions to plot some images and to make the video. So I just have to re-execute everything. Okay. Okay, so the first bit here, you can just time your function, simulate and save chunked. But if you choose to do the whole process, you can also. So here I initialize my arrays. I just use imshow to see the initial concentration. So here I have an array of U species, and I put a drop of V at the middle. This is what the init arrays function does. And I just time the execution of this function that we made. So it's, yeah, one second. This will be our reference for the rest of the CPU class. And we will try to optimize this version using other techniques. So with SciPy, we're going to try, with Numpy, then with JAX. And then for the GPU class on next week, we're going to see other techniques as well. So, okay, let's plot the images we produced and the video we produced. So here I defined just 2 images. I chose to only produce 2 images, so the video is going to be very short. But okay, let's try. Normally, I have a directory here, results, in which I have, whoops, it's a bit, how do we do? Well, it's a bit big, but this is my first image. Where is my, okay. So this is the first image I produced, and then I apply Grayscale 30 here 10 times, and I see the evolution of the concentrations here. So normally the V species is going to diffuse a little bit, but here we still don't see it because we don't have enough images and enough steps. Okay, and this is the video. So if you do it on your laptop, you should be able to open it other than in the Jupyter Notebook. If you do it on Must, I'm not sure you can open it. Yeah, in the end, maybe we'll try to retrieve it. In the GPU class, we can retrieve it with SCP. On the CPU class, I guess I'm just going to show you how it, what is the video. Okay, so let's try maybe to do, we can put like more images and more steps. Okay, let's try 10 images and these steps, I don't know, maybe 20. Okay. Here, just notice that the chunk size we use is 2 because we only had 2 images. Here I'm going to process 10 images, but I still use a chunk size of 2. In the rest, no, sorry. Yes, I have 10 images. In the rest, we're going to adjust the chunk size to fit the RAM. Okay, so if I plot the images from the HDF5, normally I should have 10 images that are produced. Why is it not the case? Yes, okay. So I have my images here. Let's check, for example, the 9th step, the 9th image. Okay, and here we can see that the species has started to diffuse in the U species. Okay, the video maybe we'll check it on the number part. It's going to be easier. Okay. So this is our Python implementation that we're going to use for the rest of the class. Now, why not try to go a bit faster with SciPy? So maybe you know SciPy is scientific Python. So it's a Numpy extension, and you use it in high-level scientific computation. So you can use it for complex differential equations, optimization, signal processing, etc. And so it's organized in submodules. So in our example, we are doing a convolution, which is a basic signal processing operation. So we can use the dedicated SciPy function for this in the dedicated submodule. So the submodule we're going to use is signal. So it's a signal processing submodule. So we import it. I'm going to go on my here. Okay, we import scipy.signal. And then, yes, here you can use it. So you can replace your Laplacian Numpy function with this Laplacian scipy function that will use the scipy convolution function instead of the convolution we wrote by hand by applying the Laplacian, the stencil over the whole array. Okay, so try to check maybe in the documentation of scipy for a function that can do a convolution in 2D, and then use it here instead of using our by hand computation of the Laplacian here, but it's not here. Okay, oops. So you replace all this complicated computation with the dedicated scipy function, okay? So did you find the scipy function that we need to use? Yeah, what is it? Yes, convolve. I think you can use convolve 2D in this case, but maybe convolve works also. So here, so in the scipy.signal module, you have the convolve 2D function that I chose to use here. Maybe convolve works, I'm not sure. So you apply a convolution of the stencil on U. And here you have to put same and boundary equals wrap to have the same results as what we do in our Laplacian Numpy implementation. Okay, so let's run it and check the performance, because is it faster or is it slower than our Laplacian Numpy? So normally in the tutorial, yes. So in the tutorial here, you time both executions of Laplacian Numpy and Laplacian scipy, and then you can use numpy.allClose to compare the results. So it's a function that will tell you if your results are the same. And I think you can set the precision also of this. Okay, so here, what are the results? In my computer, scipy is slower. You can see here I call time it on Numpy, on Laplacian Numpy, the first Laplacian we implemented, and it's 18 milliseconds. And if I call time it on Laplacian scipy, it's slower. It can depend. I think on most, last time I tried on the most Jupyter Hub, I think scipy was faster. It's slow? Ah, okay, cool. And so here I try numpy.allClose, and I check if both my Laplacians have the same output, okay? And it tells me true. Well, this is because I ensured that I have the right mode and the right boundaries when I use convolve 2D. Okay, so In the following section this afternoon, we're going to use Numba to speed up our Python implementation. So we're not going to use this convolve 2D function of SciPy because it's a bit slower. We're going to optimize the Laplacian with Numba. We're going to optimize the Gray-Scott function with Numba also. And I think it starts at 2 or 1. C'est à quelle heure que ça commence? Ah, ok. Ah, ok. Right. So we're going to lunch break now, but at 1:30 you can come back because there is a presentation of the satellite sites. Maison de la simulation. And then at 2, we resume our tutorial and we're going to tackle Numba. Okay? Thank you very much.
Et on y est. C'est tout bon. À vous.
Okay, so welcome everybody. This will be the last presentation of the week. So we're very happy to be here with Pascal Tremblin from the Maison de la Simulation, who is once again partnering with the Grey Scott School. We have a continuous support and involvement from the Maison de la Simulation, so we are truly grateful to have him with us for this edition again. And we're very happy that he can present what they are doing over there near Paris in France. So Pascal, the floor is yours.
Thanks a lot, Marie, for the introduction. So I will present Maison de la Simulation and its missions. So Maison de la Simulation is a unit whose purpose is to do research, support, and training to help communities, application communities, to use massively parallel architectures. So it's the French ecosystem. It means the supercomputers Ad Astra at CNRS, Jean Zé at Idris, and Joliot Curie, and soon Alice Recoq at TGCC. Alice Recoq will be the second exaflopic supercomputer in Europe. So we help people mainly on three topics: high performance computing, high performance data analytics, and also artificial intelligence. So for support, we help communities. Currently, it varies across time, but currently it's mainly, for example, support in astrophysics, for astrophysics exascale code, laser matter interaction, plasma fusion exascale codes, energy application, and physical chemistry also with in collaboration with different units in the French ecosystem. So we are really working on co-design of massively parallel simulation code, and also the specificity that we target a long-term investment on several months and usually several years, so that we can really be involved into the deep development of the codes to adapt them to massively parallel architectures. And since we are not such a big unit, we also target open source and codes that are largely that are used largely by the community. We are also doing research. On the research part, it's dedicated to computer science and applied math, but dedicated to high performance computing. So mainly 4 themes around programming models, data management for HPC architectures, high performance data analytics and AI, and algorithm and applied math. So here we are focusing on research and development in computer science and on libraries and tools that are going to be transversed to applications and that can be reused in many different applications across different application domains. And we give some example after. For training, so we are involved into master classes in the University Paris-Saclay, but we are doing also a lot of continuing education around COCOS. That is also present in the Grey Scott School this year, quantum computing, iOS, debugging, workshop on school. So of course, Grey Scott School, but also other school in CEA, EDF, in RIA as an example, but there's also many others. And we have the training room in which we are hosting the Grey Scott School right now, on which I'm doing this talk. For the ecosystem, so I give briefly an update. So we are in the Paris region, so at Saclay. So we have one site that is close to CEA Paris-Saclay Center, but we have also some offices at Idris from CNRS. So we have also joint people in between Maison de la Simulation and Idris. So we also work closely with CNRS. And our supervision bodies are CEA, CNRS on the universities, Versailles, Saint-Quentin, and Paris-Saclay. We have also collaborations local with Sorbonne, École Polytechnique, for example, the National Supercomputing Center in France, CC-FR, of course, Centre de Competence in France. And we also have a lot of international collaboration, mainly with RIKEN, Jülich, so the Supercomputing Center in Germany, in which they have the first exascale European supercomputer Jupiter. And we work also closely with the Department of Energy in the US for HPC. And I will give some example on how we do that. The main strategy of the lab. So if we go a bit more into the scientific and scientific challenge, we are focusing first on transition to exascale in HPC. Then also the upcoming of AI in the landscape, and also two axes that are more prospective about brain computing and quantum computing. So for exascale, so I guess most of you know top 500. So this is a ranking of the most powerful supercomputers in the world. So we reached the exascale with the Frontier supercomputer in the States in 2021. Now the first supercomputer was 1 week ago El Capitan, but now at ISC was announced that a Chinese supercomputer took the lead right now with actually CPU architectures, not GPUs. So it's actually quite interesting because it changed the landscape of supercomputing right now. And the Chinese are demonstrating that CPU can reach the exascale with relatively actually quite good performance energy-wise. So this is quite interesting. But that being said, if we take on average the computing power that is available in the top 500, there is still a massive transition to GPUs in the recent years. So now 85% of the power, computational power is in GPUs, which requires some adaptation of simulation code to exploit these architectures. So we are deeply involved into that at Maison de la Simulation, also to prepare the arrival of Alice Recoq at TGCC, so the second exaflopic supercomputer in Europe. And we have a lot of expertise into GPU accelerated architecture since quite a long time. And we invest now in the development of the COCOS library for performance portability, CPU, GPU. So you've seen COCOS on CPU yesterday, and you will see COCOS on GPU next week. This is possible because COCOS is now a product part of the High Performance Software Foundation. So it's a foundation that is linked to the Linux Foundation. So it's a place in which all the labs can put their middleware for high performance computing, so that it gets a neutral place in which we can invest on common developments. So COCOS was originally developed in the DO in the US, but now it's really part of the HPSF, which allows the European to invest in this software stack. On HPD and AI, so of course, one big change in the current architectures and also with GPUs, there is traditionally an increase of the gap between compute and memory transfer. So that is represented in this plot with the ratio of flop per byte in different type of architectures. So with the CPU trend, the increase was a factor 4 per decade, but there is a big jump at the GPU era with a big increase actually of this flop per byte on current architectures, and the trend is also accelerating a lot at 6.6 per decade, which means that we can compute really a lot on current architectures, but it's more and more difficult to extract information and extract data in the memory and then onto storage disks. So for that, we are developing some specific tools to tackle exascale era with that. Oops, I have a problem with the mouse, but I'll keep that way. The other trend is that more and more power is now dedicated to AI workflows, of course. So this is, I think everybody have seen this type of plots in any case. So AI, there is also a big push into using AI on supercomputers. So on that, we are developing two axes. So first, I/O and in-situ data analyzing tools. So this is done in the French ecosystem through what we call PEPR. So it's a program at the national level to develop the software stack for exascale supercomputers. So it's called Numpy in France. And we are developing tools to manage this I/O and to do some pipeline to do in-situ analysis so that we do not have to get out the data of the supercomputer while the simulations are running. So it's called PDI on DESA. And the second part is that we are doing post-mortem and in situ AI analytics with an image wall in a room that we have at Maison de la Simulation. And then for AI, we are also supporting the deployment of generative AI at exascale, so foundation models, agentic AI. We target specifically AI for science at Maison de la Simulation, as this is done for Euro HPC project Minerva, that involves also the main supercomputing center in Europe. Of course, green computing is quite important. So you can look, at the top 500 with the increase of the computing power of supercomputers, but you can also look at the ratio of the computing power to the energy consumption, so the flop per watt. This is also an important metric to get the most efficient architecture possible. So the recent trend was that we could achieve a really big performance or the good energetic performance leveraging GPUs here in the red dots. And the CPUs, the blue dots, were not as efficient as GPUs. Of course, now we have so the Chinese supercomputers that is changing a bit this landscape. So it will be interesting to put the Chinese machine in this plot, which I have not done it yet, but we'll see how it goes. But for us at Maison de la Simulation, we are exploring that from a different angle. So we are also looking at different type of architectures that can leverage energy efficiency. And for example, we're exploring data flow architectures like FPGA, because they are very low consumption. Normally, they are used into system embarqué in French. In English, I forgot. In cars and stuff like that, and it can be very low consumption. And we can use this type of architectures also for HPC. The problem is that the programming model is very different because this is data flow architectures, but we can reach interesting also energy efficiency with this type of hardware. And last point is quantum computing. So there is a big increase into the capacity of quantum computers with the increasing number of qubits. We are also quite interested into that in the French ecosystem. We have two quantum computers that have been installed at TGCC at CES. So Pascal machine on the Candela machine, so Ruby and Lucy at TGCC. So it's a technology based on neutral atoms and photons. And we are looking into, at Maison de la Simulation, into applications and the programming models of this type of quantum computer. So we are currently mainly working on quantum many-body problems, especially for nuclear physics. And we're also quite interested into the PyMath sides with, for example, quantum-inspired algorithms. And that's it for me. If you have some questions.
First, can we have a round of applause for Pascal, please?
Yeah.
Thank you,
Pascal.
We have
Thank you very
the
much.
whole room applauding here. So, and we are going to take some questions.
Hi, thank you for the presentation. I was wondering, at exascale, what, like you mentioned, this China has this CPU supercomputer. What seems to be the determining factor for power efficiency when it comes to the exascale? Like I know, for instance, in GPUs, you have different things that may impact the energy efficiency. I would imagine that GPUs are more energy efficient when it just comes to compute, but how is it on exascale?
So yeah, it's still an issue at exascale because for the actually, if you look at the Green 500, so the ranking in terms of energy efficiency, smaller machines are usually at the top of the ranking. Now it's actually the first at the Green 500 ranking is a French machine at CalMIP which is smaller size than exascale, and it's because you can be on smaller machines more efficient in terms of cooling. So for exascale, since it's a very large machine, it's still an issue. There is a decrease, I think, a bit less than a factor 2 between a small and a big machine. Because of that, it's more difficult to evacuate the heat. So this is the main factor, and it's to the energy efficiency. It's how you can cool efficiently the hardware, and the more you pack hardware closely to do a supercomputer, the more difficult it gets to get the heat out. So it's typically the problem for all architectures. GPUs were quite efficient into packing a lot of computation into that you can do with this type of hardware. That's why there was a gap in efficiency between GPUs and CPUs, and we call it rich exascale with GPUs. Also nowadays, these issues, it's still, I think, a problematic for academic communities. Most of the application communities that I know, they still worry a lot about energy consumption. But now with the AI data center, I think that in the society level, and depending on the countries, is not so clear for the moment. But maybe the concern will come back relatively soon, seeing the problems we have with climate change and also with energy consumption of big data centers. Anyway.
Okay, thank you, Pascal. We have a second question here.
Yes, thank you for the presentation. Are there any ongoing projects on how to reuse the heat produced by the data centers, for instance, within heat networks?
So yes, there is usually, for example, I know that this is the case at IDRIS, at TGCC. It's coupled to local areas to be able to reuse the heat. So it's definitely something to do, and it's very good to do it. Still, it has some difficulties because it can work in winter, but of course in summer you do not need that much heat anymore. So it's actually not difficult to have something that is efficient all year long. Possibilities is also to go into areas where the climate is cooler, like in Finland with Lumi. It's a possibility also to use locations that are really north to be able to cool also more efficiently possibly.
All right. Thank you, Pascal. I think we're good here in terms of questions. I'm not seeing any hands on the right, so a round of applause for Pascal once again, please. Maybe one after. Okay, Marie. So.
Okay, so thank you very much, Pascal. If you have any questions for him, you can still use the dedicated channel on Discord, of course. Thank you for partnering with us again. It's really a pleasure to work with you. And now we head into the final afternoon of this CPU week. So everybody, let's meet at 2 p.m. and let's finish strong. So see you soon.
Thank you.
Thank you.
Okay, we are back here on the Grayscale School. So we continue a bit of wizardry with Alice on Python, and then we will move on with Sébastien with all wizardry in Python, and then the operating system, which is bothering you, of course, for the allocation and the performances. So Alice, it's up to you.
Thank you, Pierre. So we're going to take back the tutorial we started this morning. I repeat here the instructions to install it if you haven't done it already. So you just have to clone the repository. I think the link is in the Discord. And if you want to open the Jupyter notebook, as I do, you just run pixie run Jupyter Lab in your command line. If you're on the MUS cluster, you can also run a container on the MUS cluster by clicking this link. But okay, from source on your laptop, it's easy to do. You don't need a fancy CPU to do it. We're not going to run benchmarks or anything, so you can do it on your own computer. For the GPU session, we're going to need the containers, but for this session with Pixie, it's all taken care of. Okay, so this morning we saw the Python implementation of the Grayscale reaction, and this afternoon we're going to see how to optimize it with Numpy. If we have time, we will talk a bit about JAX, which is another library, but we will implement the Grayscale reaction with JAX probably next week during the GPU session. Okay, so let's start with Numpy. So first of all, you remember all the functions we defined this morning. We put everything in a Grayscale utils module. So you just have to import it to have all the parameters, the functions that we use to initialize the arrays, to make the videos, etc. So you just have to import it. These functions are just helper functions, so we are not going to optimize them. We're going to optimize the heart of the computation, so the Laplacian, the Grayscale reaction. So the rest you can just import from Grayscale utils. Okay, so I'm on the 4th notebook in the tutorial directory. Try to run the cells with me so that you can check if you have any issue. So how are we going to optimize our Python implementation with Numpy? Well, we're going to use the fact that Numpy is a JIT compiler, so it means a just-in-time compiler, and it will translate our Python and NumPy functions into optimized machine code. And it will use the LLVM library to do that. So with Numpy, we can compute in sequential and multi-threaded. We can also compute on CPU and GPU. In this session, we're going to see sequential and multi-threaded for CPU with Numpy. So Numpy is a bit different than other optimization libraries because it works best when you have a lot of loops. For loops in Numpy are really easy to optimize. And if you use NumPy a lot in your code, it will also work well with Numpy. So maybe you've already used Numpy. Usually to see if your code uses Numpy, you see this this decorator here, JIT or NJIT. So if you have this above a function, it means that this function is going to be JIT compiled by Numpy. You have options, for example, no Python equals true, parallel equals true, and fastmath equals true. So we're going to see it afterwards. But so how does it work? So when you put this decorator on top of your function, then Numpy will read the Python bytecode for your function, and it will combine it with some information about the types of the function's arguments. And then it will use the LLVM compiler library to generate some machine code. So this is an optimized version of your function that will be put in the cache. And so the next time you execute your function, it will use what is cached to execute your function. And so you don't have to compile it every time you compile it. and then the result is put in the cache, and you can use the faster machine code. So what you have to bear in mind is that whenever you are going to execute your function, the first execution will always be the slowest because you will have this compilation process that is going to be done. Okay, so maybe let's try to transform our first function, the Laplacian Numpy function. We're going to transform it to use number and to optimize it with number. So just run it, import number, normally it should work. And then, yes, okay, so you take the same this function here, and you just have to optimize it with number. So to optimize it, basically, you have to put the JIT decorator to JIT compile it, I think. Yes, probably that's all you have to do. So if you want to check the solutions, it's in the solutions repository, and you have the corresponding solutions here. So, well, for this moment, it's not going to be very complicated, so we can do it together. So now to optimize this function with number, all we have to do is decorate it. So we imported number as NB, so we have to call the decorator nb.jit, and we had some options here: fastmath equals true and cache equals true. You can check the number decorations for the options that you may want to use. Fastmath is to relax the rules on the computation, on arithmetics, I think. And cache here is specific to number, and it means that you're going to cache the compilation of your function. I mean, the results of the compilation will be cached. This can have some problems if you, for example, recompile another function that has the same name, etc., or if you change your function and recompile it, then you can have some issues, but it's all described in the number documentation. And for this part, using cache equals true for us, it will work. Okay, so basically what you just have to do here is to add this number.jit, and I think that's all. And now to time it, how are we going to do? We time okay, so we just run it once so that the compilation is done, and then we can time it. Okay, because if we time the first call to this function, it will take into account the compilation time, and the first iteration will be much slower. So here, what we have is 87 milliseconds. And I think for our Python implementation, it was a bit faster before. Yeah, there is a question?
Why is the function compiled at the first execution and not when it's defined?
When it's defined, but you have to use it for it to be compiled.
Yeah, but why does the library not compile it just when we define it?
Because it will compile a different version. If you change the arguments here, it will compile something else. Okay. If you change the type or the, yes. So this is why cache also can be a bit tricky sometimes, because it will cache something, and then if you change the arguments, it might be a bit tricky, yes.
Okay. Thank you.
You're welcome. Other questions? No? Okay. So basically what we just saw is that when we try to just JIT compile our Laplacian Numpy, it's not good performance. I think for the Python version, maybe I'm wrong, but I think it was a bit faster, the Python version. Okay, yes, thank you. So why is it slower when we try to optimize it with number? So our problem here is that we use extensively NumPy in our Laplacian Numpy function. And when we use number, it can be better sometimes. It's not very straightforward, but it can be better to have explicit for loops. So here is the documentation that says it. So in Numpy, a good performance tip is to use for loops and to optimize them with Numpy. So what we're going to do is to write a Laplacian Numpy version specific for Numpy that we're not going to use without Numpy, because for loops in Python it's better to get rid of them usually. But with Numpy it's okay. So let's write a Numpy version of the Laplacian, getting rid of the Numpy broadcasting. You remember we broadcasted the computation over the whole U array. And so this we're going to get rid of. And we were going to replace it by for loops over the rows and the columns of U. Okay? So I don't make you write it because it's a bit cumbersome also. So these are the two loops that you defined this morning, the loops on the stencil rows and columns. And here we're going to add two more loops to apply the computation to the rows and the columns of U, okay, instead of broadcasting it like we did with Numpy. So this is basically a non-Numpy version of this Laplacian. We JIT it with this as before, and then let's try to run it and see whether it's faster or not. So here you see I still called it before once and then I ran it. Okay, so it's 10 times faster, I guess. Yeah. Okay, so this is an example in which for loops are good. It's for Numpy. But usually we try to avoid them by using Numpy broadcasting. In this example, it was a bit better with Numpy, a lot better. Okay, so now it's your turn. You have you have this function that you have to optimize with Numpy. So it's another version of what we just wrote here, but instead of keeping the loops on the stencil rows and stencil columns, we are going to unroll the loops. Okay, and this will also give us some acceleration. Ah, on voit pas? Agrandir. Quoi? Ouais. Ah, voilà. It's better? Okay. Okay, so I give you a few minutes to test what we just said and to optimize this function as we did for the other ones. So it's already unrolled, you just have to JIT compile it with Numpy, I guess, and that's all. So try it and then we'll see together, okay? Are there some questions on this part? Yes, question here.
So basically, we are not using Numpy anymore. Does it mean that we lose the benefit from SIMD?
Sorry?
Does it mean we lose the benefit from SIMD? We cannot use that once we use this number JIT.
There is some echo and I cannot hear, sorry.
So does it mean that we lose the benefit of SIMD?
Do we lose the benefit of SIMD? I'm not sure. I have to check and then I'll tell you. Okay, so I think what you just had to do here is to, where is it? Is to add this as before in the top of your function. And normally if you run it, in my test it was faster, but I saw some people here and for them it was not faster. So let's try it. Okay. All right, so in my case, it's a bit faster, but not much actually. So you can choose either one, this one or the one above. And then if it's easy for you and you want to go a bit deeper, I suggest you do this, this exercise here. So if you are a bit behind, don't worry about this exercise, but it's just to show some vectorization stuff. So in Numpy, you can check the assembler code that is produced by Numpy. For this, you have, though, to compile your function with the cache equals false. Okay, so if we want to inspect the assembler code, we're going to recompile our functions and remove the cache equals true that we put. What we can do is check if our operations are vectorized in our optimized versions. So for this, we can look for hints that the instructions are vectorized. So here, you can look for an addition that is vectorized or multiplication that is vectorized, and you can look for vector registers like this one or this one. It depends which type of vector registers you have on your computer. Okay, so if you want to do this exercise, you can just define a function that will inspect your assembler code. For this, you have to use the inspect ASM function from Numpy. Okay, and then you produce a text file, and then you search in the text file for vectorized operations or vector registers. So you can try to do this exercise. Remember that you have to apply this on functions that are not compiled with cache equals true. So you have to recompile your function. And then, yes, you can use it here on your Laplacian Numpy and then on your Laplacian Numpy and check which one is more vectorized. Okay, so I'll give you 5 minutes to do it maybe. And then we will optimize the rest of the Grace code reaction with Numpy. Okay, once we are done with this stencil comparison. Are there some questions? Yeah, sorry.
It's JIT compiled, right?
So what?
It's JIT compiled.
Yes.
Yeah. What is the backend? Is it Clang or LLVM?
LLVM. Yes. Sorry, it's here. Yes, it uses LLVM.
Okay, nice.
On the Discord, can I check the Discord? Ça va? C'est ok? Je peux faire ça? Ok. Yes, okay, so there is an answer about the SIMD question. I don't know if you saw. It doesn't use SIMD per se, Numba, but it lets LLVM apply SIMD. Okay. Okay.
Do we have a control over how good is the optimization level? Can we select the optimization level of the compiler, or is it by default 01 or 00?
I don't think it works this way, but I don't know. I've never tried to set the level.
I guess so.
You have some keyword to configure the optimization, like fastmat. We don't have the list of this option, but they exist.
The options, I guess you can find on the Numba. Yeah, you have the options, but to JIT compile, but I'm not sure I saw some options over compilation level. It's a manual. Compilation options, yeah. No, I mean, it's not in the doc, but so maybe there is one, but they don't put it in the user doc for everyone to see. I don't know. Another question? Yeah.
Another question I had is, when you compile in C or C++, the interface of the beginning, the way you divide your code into functions doesn't matter that much, because the optimizer can refactor your code to produce a faster assembly. Is that the case with Numba, or or how you define your function will affect what the compiler can do?
Yes, because you JIT compile a function basically. I think you can also JIT compile classes, but you JIT compile something that is restricted, and so you can have some problems. Some functions you cannot JIT compile them because you don't have the right type of arguments, like some arguments change or inside the function or something like that. So it's better to have small functions that you JIT compile. I think maybe the last function that we have, we cannot JIT compile it. The simulate HDF5 stuff like this, we cannot JIT compile. Yeah. So yes, it works by construct. Okay, so let's check the answer to the exercise maybe. Where was I? It's here. Okay. So it's an example of a function that you can use to inspect the assembly code, but you can write your own. So I'm going to execute it. So it's looking for SIMD AVX. Yes, and also for scalar, so scalar register and scalar operations, okay, to compare. Okay, so let's try it with our Laplacian NumPy. Yeah, so here, maybe I didn't explain this. To have the assembly of your function, you have to call it like that, func.inspectAssembly, okay? And this works if you JIT compiled your function with Numba before, of course. So here is the answer, what Numba gives us when we JIT compile our Laplacian NumPy function, okay? So you see, there is a lot of scalar operation. A lot of scalar registers are taken here, okay? And we have some SIMD, but not much. And now let's check the same thing, but with our Laplacian Numba that we wrote specifically for Numba. Okay, so we have fewer operations, first of all. We have more SIMD, and we have just a few scalar operations and registers that are used. Okay, so this is an explanation of Why our Laplacian number is much faster than the Numpy version? Because we use a lot more of the SIMD capabilities. Okay. Okay, so now I guess it's your turn. You can use number on the rest of the functions. Well, here you don't have to do anything. I don't know why. Okay, so this we can also optimize with number. So we put our JIT here on the Grayscale steps. So this is going to JIT compile this function that it takes a while to run. So hopefully it will help us. This function you can also JIT compile it, I guess. This function probably also. And this one we will not JIT compile it because it uses well, a lot of things that are not easy, external libraries and stuff like that. Okay, so try to JIT compile the functions and then test everything with this this cell here, and then you can check the performance and make a video. Okay. I guess I'll leave you maybe 5 to 10 minutes to do it. Okay, you just have to add number.jit on most of the functions. Okay. I'm going to check if there are some questions on the Discord. Okay, no questions. So I think most people are done. Let me know if you didn't manage to do this part. So if we want to optimize our grayscale reaction, we just have to add this. Okay, this is the same for the reset borders. I mean, it's not a function that takes a lot to execute, but it's still an operation about on all the borders of an array. So let's JIT it. This function we can also JIT it because it's pure NumPy here. I mean, we don't use any external libraries except NumPy. And we don't have anything to change, yes. So we just JIT it up. This function, we are not going to JIT compile it. Well, because first of all, it uses external libraries. If you were to JIT compile it, you can try it, won't work, I guess. It will tell you that it's not possible because you use HDF5 and stuff like that. So we just leave it as it is. Okay, and now we can try to run it. So let's take, here maybe I was a bit, we can take a little bit more steps. So let's take 10 steps between each image and 10 images to produce. We are going to run it once and then run it again so that all the functions are compiled in this execution, and this one is a proper benchmark to be run. Okay, let's do this. It should be faster than the NumPy implementation, but you can compare. Oh. I have a bit of a problem. Okay, so here the chunk size I have to adapt because it was a bit too high. And then you can check that your HDF5 file contains actually some result. And then you can make the video from the HDF5 file. If you are on your computer, you can check the video. If you're on the MUS cluster, I don't think you can, unfortunately. But I mean, we should all have the same. And so, yeah, let's check the video. Where is it? So here I'm on the repository that you must have cloned from the GitLab. I go to CPU, results. I have my 10 images no, this was from before. Okay, I have my video that I just produced here. Can I open it with that? Oops, no. Okay. Let's check the video together and see if we did something wrong or not. So results. I didn't call the function to produce the images, so I'm not going to have individual images. But here, yeah, I have the beginning of my video. So it's only 10 images here. Okay. I can produce more, but it will be slower. So for now, I'm just going to stop with that. So we produced a tiny bit of video with Numba. Now we can try to go even faster and use Numba's capacities for multi-threading. Okay. So with Numba, you have some options to parallelize, to multi-thread your computation over your code. You can also choose the number of threads that you want to use, but by default it will take all threads available. So I do not change it here, but if you want to change it, you can. To do this, what you have to do, oops, I'm in the solution one, sorry. What you have to do is use Numba's p-range, okay? So this is a way to multi-thread a for loop. Instead of doing for I in range, etc., you do for I in p-range. And this will tell you the content of this loop will be multi-threaded. And so each thread will take another value of I. So here, in my Laplacian, so if I take the unrolled one that we had before, what I can do is use p-range in here and in here to say that for each row and for each column or of my array U, I can have a new thread that will compute this portion of loop, okay? So try to do this. If you use p-range, you also have to specify parallel equals true when you JIT compile your function. So basically, this is the two things that you have to add. Parallel equals true when you JIT compile, and p-range here and here. Okay, and then you can time it and see if it's faster than the sequential version or not. So we're going to do it together, I guess, because it's not very hard. So here I put in my JIT decorator, I put parallel equals true. I also put p-range here and here to say, okay, the content of this loop will be parallelized. And then I can time the execution. So depending on the number of threads you have available, you will have some different results. So, well, I call it once to have the compilation time, etc., but then I properly benchmark it. And what do I see? I see that mine is not faster. Okay, too bad. Did you try this? If you tried and you had something faster, can you tell me? Normally it should be faster. Okay, maybe I'm not using the threads, I don't know. Okay. On Must, last time I tried, it was faster. Okay, let's do the same for our loop in the Gray-Scott function, okay? Because we have to do a loop over these steps, so like 10 or 32 steps of time. Let's parallelize that as well. So we compile it again. Oops, okay. We compile it again with parallel equals true. And then we're going to have to add the p-range in here, I guess. Yes. Well, I forgot p-range. Okay. Sorry. Okay, and then you can try to run it. Where did I forget that? Okay, so now I have something faster, yes. Okay, but only 2 times faster. Okay. I check that the results are the same. In my case, they are not. I don't know why. Maybe I would have to adjust the tolerance. Maybe, yes, the order of operations is important. Okay, well, it doesn't matter. For the next function, yes, I think you don't have to do anything. Yes, we're not going to, yes, okay, for this function, the only thing that you have to change is the name here, Gray-Scott G-steps. Instead of Gray-Scott G-steps, we use Gray-Scott G-steps parallel. That's the only thing I changed, but this is why we have to rerun it again. Okay, so we do this, and then we rerun our big function. Okay, and now you can run the benchmark. So run it once so that it compiles, and then run it another time so that you can really benchmark. We are going to do only 100 images, because if we do 1,000, it will take forever. I mean, you can, but I won't. Okay, so try to run this, and then you can check your video. With 100 images and 32 steps between each image, it should be nicer than what we had before. Okay? And if you are, okay, I'll do it after. If you are done with it, you can try to do this exercise. Okay, we're going to check in 5 minutes. All right, try to do it. Let me know if you have questions. Okay. Ah, there is a question here. You have a micro here.
I run it with a normal range, and it gives me the same result for the two function.
Okay.
Then I change it to a P range, and it gives me false. So everybody parallelizes. So
yeah.
It parallelizes it the calculus are the same because we change the values.
Yeah, I guess it changes the order of the operations, and then you don't have the same results at the end because you have multiple threads, and in the end you combine them differently. Yes, maybe this is why I didn't put an P range here before. Yeah, I think if you remove it, it's okay. Yeah. Okay, cool. Thank you. Well, I'm gonna remove it.
Check.
Okay, so my benchmark is still running. I guess we can check the correction for the exercise, if some of you checked it. So it's just to check the number of CPUs that you use when you put Numpy in parallel on your computer. So by default, it should use all CPUs available. So you can run that. I can't because I'm still running the benchmark. But yes, here you can use this function here in Python function that will give you the percentage of CPUs you use. So if you use more than one, you should have a percentage that is higher. So if you have 600%, it means you use 6 CPUs. So you can try to run it and see the result, and normally it should correspond to the number of CPUs you have on your computer. And if you want to adapt the number of threads that you want to create, you have a set number threads, I think, in a Numpy, which is an instruction that you can give when you, I guess, when you call a function. Okay, so my benchmark is finished. So you see, it took me 8 minutes to run my benchmark, and wall time 1 minute. So I guess I have 8 CPUs probably on my computer. It's a bit slow, it's Python. But with JAX, I think we're going to do faster. For this, you're going to have to come back on Tuesday because unfortunately today we will not have the time to implement Chorus code for CPU on JAX, but we will do it on Tuesday because basically for CPU and for GPU, it's the same thing in JAX. You don't have to change anything. Okay, and so let's try to run this and see how many CPUs I used. Okay, if you have some questions on Numba, don't hesitate to ask them. And then Jean-Marc will give you a brief presentation of JAX so that we can get started on this, and then we'll see the rest of the JAX class on Tuesday. Okay, I'm still running this. Did you manage to run all the cells with the parallel instructions? Yes? Okay. Are there some questions on the Discord? Okay, so someone has 600.5 maybe, 650. So I guess you must have like 6 or 7 CPUs, maybe 7 that are not used at 100% each, or maybe 8 even. Yeah, I'm gonna check mine. Okay, I have 8 CPUs. Okay, so I use almost every CPU at 100%. Okay, so that's it for Numba. If you have some other questions, I can answer them in the Discord probably. And now Jean-Marc will present JAX. So you can take the 5th notebook in tutorial, and this is going to be the rest of the class for today. Oops. Okay.
Thank you, Alice. So now we speak about JAX. So what is JAX? JAX, it's a Google development of a Python library for machine learning, Numpy type, and array-oriented computation. It is an ecosystem geared towards the deep learning. The Flax library are the best known. And it's an equivalent to of Keras, TensorFlow, or PyTorch. And you can find a list of projects based on JAX. Yeah. With additional library and so on. JAX is designed to support several accelerators without code modification, parallelize and distribute calculation across several accelerators, provide a powerful automatic differentiation tools. It's useful for statistic project, and use JIT to speed up processing. All these features make JAX a high performance library that can also be used in area other than deep learning. Here you see the summary of the support platform, but I think it's not updated. This is the last version. So it covers AMD GPU, Intel GPU for experimental, and it's interesting for also for Mac, Apple GPU. for last processor M1, 2, 3. So what is inside JAX? Adapted to the different accelerator type come from the use of XLA library. XLA is for accelerated linear algebra. It's an open source machine learning compiler for GPU, CPU, and ML accelerator. It is the equivalent of BLAS and LAPP for Numpy and CPy. And this open source project is maintained by the hardware industry and software also, like Alibaba, Amazon, AMD, Apple. I show you the entire diagram that summarizes how JAX is performed. So here you have a Python function with some restriction, a pure Python function you speak about later. And JAX create an intermediate representation of this function in this own language. And with this expression, you can easily apply transformation. And after the JIT compiler is performed, you have a step of optimization with HLO, with, by example, a clever factorization and so on. And as a last step, you have the implementation for the specific accelerator, CPU, GPU, TPU. Content of the JAX library. There are around 20 sub-library, including, of course, JAX and Numpy, which we will talk about later. But also, we have an equivalent of CPy, JAX CPy, contain 10 of the 14 CPy sub-library. Not all functions are present, but they may be present in other projects of JAX. For example, the submodule optimization. You can find a very good implementation with project Optax. There are libraries related to the calculation. JAX random, to image processing, JAX image. You have the low-level interface with XLA JAX LAX, and some functionality for neural network with JAX NN. You have library for development and like a debug or profiler. Library related to parallelism and hardware management with JAX sharding and distributed. We have also library related to the data representation with JAX tree, tipping, and DLPAC. So I present the JAX array. So JAX has its own array representation that takes over the Numpy functionality and API. JAX Numpy documentation, JAX Numpy documentation however, we have some difference. For the example, with init and conversion. So you can define a JAX array from a Python list, but you cannot, for example, use directly JAX array sum with a Python list. Now we produce an error. A type error. For the Numpy library, it's okay. You can convert JAX array to Numpy directly with the array function, and you can convert Numpy to JAX with the same function, but from the JAX Numpy library. Here you can see the JAX type. Instead of in the array class used by Numpy. You have some difference with the possibility of array. The JAX array are immutable, and for example, you define a JAX array with value 1 everywhere, and if you want to change the first value, you cannot with the same syntax of Python. So the workaround is to use, like say the error message, you can use method at point xx for family function. So to do the same thing with JAX array, to replace the first value, you must write like this. So at index 0, set 0. But the function return no error, but the array is not modified. If you want to modify the array, you must add this assignation to really change the value. So it not seem very optimal because a copy is a priori made, but in a JAX doc, he said when we apply JIT decorator, the compiled function, this expression is guaranteed to be in place. So it's something to know. So with the method at, you have a lot of function. You have the list here. So set for assignation, add, subtraction, max, min, apply function, universal function. You can call function for all data returned by x at, and setter function. With JAX, we have no index check. If your index is out of the range, no error is raised. So return 4. So you don't have the protection like Numpy array. Now some definition. What is the transformation for JAX expression? And so a transformation, it's a function that transforms a function in another function. The typical example, it's a JAX grad of a function f, which returns the application derived from f. The following function are the main transformation. So JAX grad, JIT. JIT is a transformer. It transforms a pure function into a function in a JAX expression. And another transformation is VMAP, for automatical vectorization of the function. You can combine the transformation. So you can, for example, create a JAX JIT of grad. So an example of the expression of the grad function in a JAX expression. So he takes this function, he creates a derived function, and this line print the JAX expression. So it's a pseudocode useful to optimization before accelerator implementation. Now there are some constraints to apply a JIT function. So JIT you can apply with a decorator, with JAX at JAX JIT, or with a function JAX JIT parentheses. The first call can take time. The result it catch. So carefully, if you so be carefully to bench this function. The first execution is very slow. So when you the condition to JIT a function, your function must be a pure function. So what is a pure function? It's all inputs come from parameters. The function has no access to the global variable. They not access to a static function variable. All outputs come from the function result. There are no internal no internal change of the variable is transmitted. And output array have a fixed shape. So we have these three conditions. So in the documentation, we have a dedicated paragraph to the error written by JAX, JAX. there are another constraint. In fact, all parameters must be an array. If a parameter is not an array, it must be indicated by defining as a static argument. At the compilation stage, the JAX array change type to a tracer object which doesn't contain data, but the type is the shape of the array. So here you have a simple function. We split the array X in two parts along axis. And if you load this function, we have a jitterer. So in fact, the problem comes from this parameter. Axis, it's integer, it's not an array. And you must specify this. So we use a decorator from functools lib who dynamically fill the parameter with default value. So if you flag axis, so argument 1, argument 0 is the array. It's okay. So it's not always very clear. There are some constraints. So understand which value and operation will be static and which will be tracer or array. In fact, is the key part of using JAX effectively. In the documentation, we have also a paragraph how to think JAX to understand what is a tracer and a static variable. Okay. I finished by the vectorization after Sébastien takes the. So vectorization is very easy with JAX with the transformer VMAP. With the first parameter is your function, and the vectorize is along the axis. For example, you can vectorize the convol 2D function for many image. So here you have a sample kernel, and here you have the vectorization performed with loop. And this piece of code, you can write a very with a few lines with VMAP. It's equivalent. So I don't have the time to enter in the details. So I pass to the conclusion. So learning feedback of the all Numpy API LACK. JAX is a pure test, in particular slicing in place mechanism. JIT-JAX is not at all like JIT number. In particular on loop management, it's necessary to manage large loop with control flow, operator of lib JAX LAX. Otherwise, performance is degraded, and pure function and management for tracer and static variable will require learning. When you have identified all these false friends, the performance seems to be there. The combination of transformation JAX, VMAP, function, composition is powerful, and powerful with a short syntax. It allows to use all CPU, and above all the code is ready for GPU. So next week we will see a JAX for GPU usage. Thanks.
Ouais. Ouais, ça me fait l'intro. We have the screen. I need to boot up my slides. So hi everyone, we'll come back to memory. I will take some minutes to discuss memory about Python. Because there is some interesting things to see there. Python. Okay, memory optimization about Python. I will not take too long. I will just show some metrics and show some numbers to see where we are with Python about the memory accesses in terms of performance. And I will show that with Malt we can find some examples. I have provided all the code, I mean my own implementation of Grayscale in Python in the memory container. I'm a bit sorry, it's not yet in the Python 1. So if you want to get it in the Python 1, you need to git clone. I will give you the command in the Discord if you want to play. Just after that, I will first discuss a bit, and you can play by your side if you want after. Can we compare the Python version with the C version? Because this is not what we did up to now. We compared the Python version with the Python version. And if you look a bit clearly, this is on the cluster here at Annecy. If we run the C version with the pyramid, so the fully optimized one I have, we are really at 0. I don't know exactly the value seconds. If you are running sequentially in C, we are kind of relatively a bit slower. Remark that here we are not very efficient for a small problem on the machine, because the problem is too small to use so many cores. But I present here the results of the Numba and the Numpy versions I had last year, which is the version we presented a bit less optimized. And we are a lot slower, kind of. So we can first try to pass malt on those versions and to see a bit what it's saying. So I will pass malt on a version which is already a bit optimized, so not exactly the one I mean we had last year. There is already some optimization done. Sorry, I came here. I will pass malt. So for those who have already the memory container, you can go in. I will give in Docker in Discord the path. cd-free.grayscott memory where we were last this week for me, and this time we will go in the Python directory. In the Python directory, if ever you want. So in the memory container we had used in the past. So maybe don't lose your time. I have 15 minutes to present. So if you want to play, you can play it during the pause if you prefer. So otherwise, we will be a bit late. I will give the slides so you will be able to read it. So if I do malt./main.py -o and I take the numpy JS grayscott 2025, and I will take an old version of the parameter set, params equal old. Zoom, thanks. I need to zoom. Normally I have everything. -s, I will make, I don't know, 1,000 steps. Let's go. It will be a bit long, huh? This is Python. And in addition, malt adopts some overheads. No, sorry, I made malt-python I should use. Python is slow, and I'm adding a bit of overhead. So it will take, I don't know, 30 seconds, something like this, to profile. So here we can see I'm using the NumPy Laplacian of my implementation, the NumPy stepper, which is a very simple stepper, and the basic runner, so no cache blocking and nothing I will show after. And the old parameter set, so because we made a mistake in this one last year. I should have made the progress bar, but yeah. Python is slow. No, and malt also adds a lot of overhead in practice, because let's say that in Python, mostly every line is giving some mallocs. So I get a lot of mallocs in practice in my head. So I need to handle that. Also, there is no efficient way to get the call stacks in Python. Not at least not as efficient than in C. Yeah, dumping the profile. Come on, please. Yeah. Malt-webview -p because I need to change the port, otherwise I have a conflict with VS Code. -h because I don't know why on this cluster I need to give the host address I need to listen on, and the profile file. Malt.json. Up, I'm going to the web interface. Of course, I need to take the token, which is here. Up, token. And I'm in the interface. So I'm going to look on the global statistics. And normally you see some red numbers. Allocator pressure. The allocator has received some requests about memory, about 186 gigabytes of memory. So not an instantaneous value. It's using probably a few megabytes in practice, but it's a kind of making malloc, free malloc, free malloc, free malloc, free with a big array. which is arriving so many times that it's quite a lot in practice for the allocator to manage. We recycle our memory 23 times, so the memory is going up and down many times. So probably when it's like this, it's saying to check the allocation rate. So I will go to the time analysis, and I will go to the allocation rate, memory size. So here I have a big thing at the beginning. Okay, 46 gigabit per second at some point, and then it continues 3 gigabit per second. So all the time, every second, I'm giving 3 gigabytes to the system and requesting 3 gigabytes to the system, from the system. So we might want to search from where it's coming. For this, we can go in the home page, and you remember that at the home page, I have some top functions for several metrics. So here there is a allocation count, so the number of allocations. Most are hidden in the import part of Malt, so I don't care too much. And in the cumulative allocation, the sum, which is a metric which I am interested in here, there is a pi. So in Malt, all the Python functions are named pi column something, just to distinguish them from C. And here there is a function which, in terms of summing all the mallocs it has done, has made 139 gigabytes. So we can click to go to see what it is doing. And this is this function. 139 gigabytes, not megabytes. That's quite a lot. So here we are seeing 2 for loops. Okay, we are. This is an old implementation, so they made a better one this year for you, of course. Laplacian. So we try to not make some copy by using some quotes. I mean some braces. And then I'm doing plus equal. One multiplied by something, so this probably I can remove because it's useless. Stencil multiplied by u. And using some braces, so normally I try to not make some copies, so here I have some copies. What I made as mistake. So many mistakes, there is 3 mistakes here. First, there is this one multiply, which is useless, so maybe it's not a problem of performance, so we can remove it. But here there is a plus equal and a multiply. And if you do that, Numpy decide to make some copies. So how to write it? If you want to write it in a better way, you can write it like this. Sorry, there is not a solution yet in the container. I need to put it. I will send it in the chat. So I need to write it again. Allocate a temporary array before the loop. So I zoom again. Let's remove this in the part. So I allocate another temporary array to make my multiplication, to have an output value. I'm calling np.multiply, which is the function which has been explained by Alice, I think, before. So np multiply has an output parameter, so I can say compute this and put the result inside this, which already exists. So normally I don't have any copy. And I plus equal after that. Okay. From this, I can win a bit of time. I mean, at least avoid the allocs. So maybe we can copy paste and see if it's avoiding the allocs. Where I am. Here. I copy paste and I will run again. So in practice, I already removed some of the equivalent allocs problem we had in the code. So normally, when I started with the code from last year, I had several points like this where there was 100 gigabytes of memory at several places. So if you have at one place, depending on the size which is allocated all the time, this is fine because it stays in the cache and okay. If the problem is small enough, it's not a problem. And here, for example, in terms of performance, it's not a very big problem, but a little bit. If you go in 4K, this is more. So this is just an example to see that with Malt, you can find in Python some performance problem in practice to see where you are making too many allocations quite easily. Because this is one of the top problems you can report with Malt in Python, from what I understood yet. dumping the profile. Of course, I get mostly a very flat call tree in Python instead of a deep one in C. So it's also slower for me to manage it. We can go in 7 something. Yep. $63 gigabytes. So already this is 3 times less. There is still some, but we have far less than before. The one which stays, it's in my multiprocessing thing, but I don't be able to make something with that. I mean, it's not my code by itself, so it's. So I try to make a lot of optimization like this, trying to track all of them and try to make some optimized version. And also there is a small mistake which has been done last year in this stencil part. Sorry, where I am. This stencil, it's declared somewhere. And you remember that Alice, when she declared all the arrays of the computation, she declared it with a float 32 type. But last year we made a mistake. If we are looking to Gray Scott, I think it's in model params. Last year we declared the configuration that way with no data type. Which means that last year we made the mistake to let all the configuration class or options in the Jupyter notebooks in a way that the stencil is not in float 32 but in a Python floating points representation, and all the constants were also that way. So I made a version. I made a version by casting all the floating points, and I will show you that we can gain a bit of performance just by doing that. And here we win a factor close to 2 just by changing this. So this is exactly what I shown. So I will not pass too much time because we are out of time. So I will go a bit fast just to show you the results. If I compare the Gray Scott with just changing the configuration, so not the allocations already, just the configuration, the floating point typing. I'm going from here in terms of execution with the version of last year to here. That's I priced just for floating point casting. So in Numpy, take care a lot with the casting because the casting made some copies and some very, very costly conversions in practice. In Numba, which is another version we had last year, and I try to optimize this year. Numba, it's I don't know why it's slower if I'm making the typing, but I don't know exactly why. Probably when I made my run, there was a mistake. But anyway, we are still far away from the C version. You agree? Very far, kind of. So I try to make to play a lot of things in terms of optimization. So like the C version, I made my parameter class to compare the new and the old one. I like this when you try to optimize something, you need to play with many versions. So I try to lay out what concept I'm playing with in layers, which represent some class in my code in practice. I have a runner, which depends on if I'm using the basic running, so just calling the kernel on a single array in one go, or if I'm making the blocking, the pyramid, the parallel blocking, etc. And I made also different Numba implementation of the kernel itself and of the Laplacian. So everything you have seen already with the discussion from Mark and Alice. And I try to play with various variants about this. And then I was able to get this chart, which is all the versions I was playing with. And I finished to find a version where, if you say here, Numba loop, pyramid, and parallel, so using threads, so parallelism, explicit parallelism in Python, plus Numba loops, plus pyramid, so the cache blocking, I'm doing to a very fast improvement. which compared to the NumPy basic is roughly a factor 25, something like this. That's a nice speed up, I would say. And we can compare to see where we are now. The most optimized version I have now, so not with JAX. I didn't play with JAX yet, so probably we can do better with JAX because it's a bit better done for that. The Numba version is the fastest I was able to get with Pyramid, so the cache blocking. And I'm able to be 4 or 5 times slower than the C version, the parallel one. That's relatively close. I worked a lot to get it. So maybe I can show you how it is done quickly because we are out of time. So I will try to not go away. Where it is. So stepper. Where is my parallel? No. Runner. I want to start from the runner. So I have runner, my parallel pyramid runner. This is the one I'm using for the case. Maybe I will zoom out a bit. So currently I tuned it only for a 4 megabyte cache. So I didn't make the options I had in the C version to play with the different sizes. This one is working relatively closely. This is exactly the same model about the cache blocking I used in the C++ version, a bit improved because I had some back focus to make it a bit simpler. So I built a data model to describe the variables I already discussed at the beginning of the week. I'm calling the blocking pyramid which generates the blocks. I'm passing on the steps, the phases, the blocks. So I have the loops on the phase. You remember the pyramid, you have the phases, the 4 phases of the pyramid, the various blocks inside, and I try to generate a table of the list of array of blocks I will compute on, and to send them to a thread pool to make some parallelism in Python. Okay, and inside this function I will call the kernel itself. So in practice, this is something going on top of the kernel. Once I have written the kernel, you have already seen with Alice and Mark, you can put that on top of it, and normally you get some nice performance. For the kernel itself, I can show you how I wrote it. It's in stepper Numba loop. There is some question, so I will take the questions. Where it is? I'm lost. I should have noticed it. This is not the normal one I'm using. This is this one. That's the problem when you get Numba loop here. So as before, I'm using the JIT notation of Numba, as you made. Yeah.
So this the timings, the C version does not include the compile time, right? But the JIT one does, no?
Yeah, so of course there is a lot of overhead in Python for the JIT, and for the blocking, the loop computing the blocking is written in Python. So this is far slower than the C implementation for this part of computing the blocks. I should loop over.
But so if you remove the compile time from the profiling, how does it compare at that point?
I didn't try to compare that. Yeah, but that's something we could. I mean, you mean measuring only the kernel itself?
Yes.
Yeah. No, I didn't try to put some measurement so deep in the parts. So for the kernel, this is exactly the same kind of kernel you have seen just the 2 hours before. I'm just using fastmath, caching true. I don't listen. You put it also, yeah. And I tried no-GIL because I'm putting the threads on top of this because I'm putting the threads on the blocks. So I'm entering in Numba in parallel. So I try to disable the GIL because I don't care here. And same for the steps here. I have directly the loop, and that's exactly the way I get the performance. So blocking plus Numba loops, as you have seen before. There is some questions here, but I see spread spool usage. Did you mean that Numba makes parallel less efficient? Yes and no. How to say? The problem is that I need to compute my blocks. I need to compute my blocks because I made the blocking. So I need to compute my blocks and then to make the threading on those blocks. And either I made it in Numba, so I made a version like this also, which is not as fast yet. And the simpler version I found was to do that way. But here you can do also with Numba by sending, I made a version where I send the array of blocks in Numba and looping on these blocks in Numba directly. But this is a bit harder to implement, so I didn't retain this version. Will these files be in the container? This is in the memory container. So sorry for one thing, in the memory container, I have installed the operating system, I mean the Debian packages for Numba and Numpy, and the Numba one is not optimized to use parallelism, etc. So opposite to the image of Alice. So I can show you how to run. You can use, if you want to run it, there is a ./main.py --bench, which will run automatically all those versions and giving you the timings for all the versions. And you will see that you see here in orange that there is a smaller value than in blue. This is by moving from HD to 4K. So if I increase the size of the problem, the Numba efficiency with pyramid is far more efficient. Okay, so we are out of time, so I will stop here. Just one thing. I tried also to make a pyramid implementation in TypeScript. You know Node.js. Who guessed the timing of the TypeScript version compared to the Python one? Huh? Worse? Who say better? Two say better. Slightly better. So now in TypeScript, this is sequential version, so I don't have parallelism in the TypeScript version. But clearly, in terms of optimization, they made quite a great job in practice. But yeah, this is just for fun. So I will stop here and let you come back for the operating system memory details about what is inside. So we came back in 30 minutes. So at 10.
Okay, so we are back with for some wizardry with the operating system now. So you will see how the operating system will impact your performances, even if you did your job well and your homework well. Sometimes things can go wrong. So Sébastien, it's up to you.
We come back to the memory world. No, I will speak mostly about the operating system on the memory aspect. I will not too much discuss the I/O part here. Here we will open a bit the roof of the operating system and try to see how it's working inside, and try to see how it can impact your performance sometimes in a way you didn't expect. Because yes, it can arise sometimes. You can have made your vectorization, your cache blocking nicely, and have some troubles due to the operating system, not because you made your code wrong. So I will first give an introduction about everything on this topic. I will then analyze in more depth the OS paging policy. Sorry, I forget one point about the caches. I will discuss more the caches in details compared to what we did now. I will discuss again the NUMA aspects, and one thing which is the page zeroing Linux Virtu Chandler. Why it's so costly to exchange all the time the memory with the operating system, because we can expect this is a non so costly thing in practice. So I make a bit of advertisement for someone else. If you want to understand everything about memory, there is a very nice document which has been written by Ulrich Draper, which is one of the developers of the glibc, which is what every programmer should know about memory. This document is going from the transistor up to the application, passing by the operating system. So you have everything to understand how the memory is working from A to Z. And it's frankly a bit long, but relatively well done to understand if you're not an expert. I made a bit of advertisement for myself also. I made my PhD on this topic, so of course there is a PhD in French, sorry, for the people remote. But for the people who understand French, there is a nice document explaining also everything in terms of HPC in some ways. So let's first speak about the operating system between the application and the hardware, let's say. So the keyword of this week, we have said a lot of things: loops, 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 loops. We have said buffers, 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 buffers. GPU, this is next week. CPU, CPU, CPU. Cores, NUMA, cycle, no, not cycle, sorry, I forgot to remove it. Vectorization, SSC, AVX, everything. Prefetchers, we speak a bit about the prefetchers, registers, and wraps. This will be next week when you will speak about GPUs. So you might have in your head that probably the performance is only everything around those words, which when you are looking on this kind of thing, you zoom on a loop and you say, I optimize this loop. When you are speaking about all those domains, most of the time, this is zooming on one part of your code and saying, I can take it out of the program and optimize it outside. This is quite nice already to do, but if you have a big program, you have to take a function per function to make it. So when you have 1 million line of code, of course, this is a bit more complex to make each function optimized separately, and we will see that the optimization of a full program, this is something else than optimizing the loops themselves, sometimes. So probably we let you the impression that up to now, the vision we have of the computer is a bit, there is an application, there is the hardware, and they are running kind of alone in their side, and you have to optimize everything to discuss with your hardware, point. So we already see with maths, this is not totally true, but we will see this is not true for many things. So you might want to send a rocket in the space, and if you don't take care of one thing, between your application and your hardware, there is a lot of big stacks in practice. Some frameworks, you might not know how they work inside. Cocos, for example, you don't know the internal details. There is some system libraries, the glibc, which is also a big code, relatively complex in practice. And most important, the operating system, which is in between your application and yourself, and the hardware. And if you don't take care of this stack, you probably finish that way. Your program will, the performance of your program will finish that way, and you will go with a very slowed down program, a bit like the Python program I have shown before. So let's try to understand how the operating system is running in terms of memory management. This is the topic today. To better understand how to interact with it and how it can impact your performance, even when we are not calling it. Because probably up to now you have the impression that if you don't do a malloc or don't do something which calls the operating system, it might not change the performance of your application, normally, in theory. But we'll see here, this is not true at all. So just to remember that in HPC, the memory became a critical resource, so of course we need to optimize it. It has a growing impact on the performance. We have seen that with the cache blocking on the Python code, I'm far more impacted by the performance of the cache usage than the other optimization, kind of, in some ways. The data movement between the CPU and the RAM is posing the problem of the memory hole. I already discussed that. And now we also have to manage terabytes of memory, where 20 years ago we managed a few gigabytes when it was gigabytes. So this is also another challenge for the operating system to manage so much memory. Decreasing memory per core, I should remove it because it's not true anymore. We tend to have more memory. But with the price of the memory today, probably it will become true again. So let's discuss about the caches. So we already discussed, I already said that to accelerate the memory, we put the caches between the treatment unit and the memory. So we have already said that. So remember that there is a L1 cache. I remember there was a lot of questions in the chat beginning of the week. The L1 cache is split in two caches in practice, the L1 for the data and the L1 for the instruction. So they don't fight each other. When you trash the data cache, you didn't slow down the application by slowing down the instruction cache. Otherwise, your application should have some problems if you mess up the two. The L2 cache is a bit larger than the L1, most of the time private to the core, and the L3 cache is shared between all or part of the cores. The numbers, to just remember, to have it in your head, most of the time the L1 is 32 kilobytes, 40 in some conditions. 1 megabyte, this is what, no, 1 megabyte, this is big for the L2. 256 kilobytes, this is what you get most of the time. Sometimes you have larger. And 24 megabytes, or even the architecture you have here at LAPP, this is 16 megabytes, the L3. 16, yeah, 16. But split in several domains for the course. So we discussed one thing we don't have discussed up to now is how the data is transiting from the memory to the cache. Okay. So let's say you want to make a memory access in your core 2 here, and you want to access the data from your memory. In practice, how it's working? The core is asking to the L1 cache, do you have the memory in the data in your cache? The cache will say no. The cache will ask to the cache on the top, do you have the memory in your cache? It will say no. It will ask to the next one, do you have the memory in the cache? No. So we need to take it from the RAM. Okay. And so then from the RAM, it will make a copy in every level of the cache. This is what we call inclusive caches, where we have a copy of the data at every level of the cache hierarchy. Okay. So there was a question about the allocation in the cache at the beginning of the week. This is exactly the answer. The cache decides for you, of course. The software does not have his hand on this part of the decision. This is the hardware who decide with some internal algorithms which are not known. And it will try to, it is forced to keep a copy at every level. For inclusive caches, there is also some exclusive. We keep a copy only at the level where it is used. But this is not what is used in most processors today. There is one thing which adds up on the cache hierarchies is the prefetcher. If you are accessing 1 gigabyte of data linearly, saying I access the first element, the second element, the third element, etc., the processor can guess that you will continue to access the next element and fetch them in advance. Okay? You are at the third element, he will try to fetch the fourth element in advance by speculating that you will use it later. And this is one of the reasons that you most of the time don't see nor the caches nor the memory bandwidth, because the prefetcher is so efficient that it is hiding for you mostly everything, most of the time. I mean, at least if you have a small amount of data and you fit a bit in the cache. You can plot something like this. So this is a plot a bit old now. The gaps has shrinked a bit over time. If you make some, you take an array of a certain size already at the beginning. Is there a question in the back? No, it's fine. If you take an array of the size which is fitting in the L1, okay, if it's small enough, if you recount the time of accesses for every element, you will be here. So between 0 and 32 kilobytes, I'm taking something like 1 or 2 cycles to access one element. Okay. If I'm growing, I'm taking a larger array below the L2 size. The time to access an element is increasing. Okay. So now it's on this processor it was 7 cycles. Already this was quite more than the L1. Huh? So if your application is running here or here, this is not the same performance. Again for the L3, same thing, and now again for the memory. And you see, now you understand why with the pyramid blocking I'm winning so much. Huh? With the pyramid I try to be here, where if you don't do the cache blocking by making the naive implementation of your arrays management, you are here. Okay, that's the gap you can have between the optimized and non-optimized code in memory, which can be a factor 20, but even more. So let's say if you use the cache, you can win a factor up to, not in every case, but 20, something like this. This is what you have on your hand if you make this kind of optimization. Where for the vectorization, it can be 8, something like this at best. So you see that memory versus vectorization, it's not so clear what is the best one to do. Huh? I mean, both, ideally, of course. There is one more thing about the caches. They don't fetch the data octet by octet, bytes per byte. Sorry, I speak in French. If you want to take an element of 1 byte, it will not take 1 byte in your cache, but a cache line. A cache line is what? It's a segment of 16 bytes, 8 bytes, sorry, 64 bytes, 64 bits. This is a cache line, so you cannot access 1 byte per 1 byte, but if you access 1 byte in your cache, you will fetch 16 bytes, 8 bytes, sorry. This is why you need to take care on how you schedule your accesses, because if you make an array of struct, most of the people already know, I will explain anyway with some draw just after that. Array of struct or struct of arrays, this is not the same performance at the end. So let's take an example. If I have an array of struct, I have my cell, U and V in our case for the gray Scott. I put it in a struct, and I make a mesh, an array, with that cell. Now, if my equation is accessing U and V, it's fine, because I'm fetching U and V in my memory, it's okay. But if I have some equations playing only with U now, for some reason, at some point, I have some math using only U, another loop later using only V. The loop which is using only U, when it's fetching the line, it's accessing the first U here. It fetches all the cache line in the cache. Okay. And in my cache, now I have U, V, U, V, U, V, U, V, and I'm using only U. What I did? I divided the cache size by 2 that way, in terms of efficiency. Okay, so I'm starting to lose performance in the cache. This is why array of struct, this is a bad design pattern in some way for the performance. It's very good for the software engineering, but very bad for the performance. And this is one of the problems we have today for the software engineering, is that the software engineering sometimes is orthogonal to the performance, sometimes. So we have to take care where we use this kind of struct. So ideally, I need to change a bit the layout to make the U and V in 2 separated arrays, and in this case, the performance is fine. Okay. If we can compare, I don't remember on which processor I was running that. If I make a struct array or an array of struct on a small code, I think the example is in the memory image, if you want. you can get this performance gap. Relatively important, huh? This is 25%, something like this already. In a simple example, this can be worse. So already the layout of your data in your arrays is very important. You should have contiguous data as much as possible for the vectorization, but also for the caches. Okay, that's a requirement. Yeah. Question? Is there some question online, by the way?
You showed the advantage of the struct of array for when you only access one of not all of the fields.
Yeah.
But if you systematically access all of the fields of a struct, is the array of struct better than the struct of array?
It's never better. It can be as good.
Okay, thank you.
It's not better because most of the time you are stuck for the vectorization with that. So for the caches, it's the same because you fill your cache the same way in some ways. For the vectorization, it depends how your algorithm is implemented. Sometimes with the array of struct, you are not able anymore to vectorize, depending on your algorithm. But for the cache, it's as good in that case.
If we have a struct of array,
yeah,
then we will fill like let's say we fill the cache. The cache gets filled with like the first U field.
Yeah.
And then isn't it a bad thing to when you have to fetch V? Isn't it better to have UV, UV, UV instead of UU and then VVV?
Yeah, that's an excellent question, and we will discuss that in another problem later. So I keep it in mind for
okay.
a few slides later.
Thank you.
Okay. Thanks for the question. Is there some questions online while I'm there? No, that's okay. So let's continue. You will see there is plenty of things like this in the cache. Chain list. Why also? Same reason. If you are using a chain list, an STD list in some way instead of an STD vector, this is a problem of the STD list. The STD list had you, if you had one element of the 1 byte allocation I was saying in an array, you are saying that you put one element for 2 pointers in the STD list. You have a pointer to the next element and a pointer to the previous. So in terms of efficiency, an STD list this is very poor due to the cache in practice. And if the cache would have been able to fetch the elements 1 byte per 1 byte, the STD list should have been kind of fine except for the pointer tracking. But due to the cache, it's very bad. Okay. Memory management. In addition, when you allocate some very small elements, the 1 byte allocation I was saying before, I was speaking about, you remember this 16 bytes of arrays, of headers sometime? Of course, when you allocate some data, let's say this is your data here, just one element P, something, in orange. The allocator has to remember the size of this block and probably where is the previous block in the memory. So for this, it adds up 2 headers elements. If you are using the glibc allocator from Linux, some others are doing other way. One element for the size of the block and one element to remember where is the next element. Okay, this is a chain list in some ways. So if you allocate 1 byte element, you have 1 byte to make your data here, 16 bytes of headers, and most of the time you need to keep some alignment for the allocator to be efficient. So you make some padding in the end to keep aligned to 16 bytes on Linux. So if you allocate 1 byte, okay, you get 32 bytes in terms of memory occupancy, which is also killing your cache. Of course, when you will access it, your cache will be penalized because there is all the headers, which of course your application don't care about. So you don't trash only the memory, but you trash also the performance of your application. This is why if you care about the performance, you need to pack everything as much as possible and make ideally large allocations and not very small ones, if you can, of course. Gmalloc, for example, is removing this header here. There is no header in front of the block in Gmalloc. This is one of these great improvements which has been done in terms of algorithm. So the case of the chain list in real life, this is pointer for the std list, plus headers, plus padding. So you see quickly that if you are using an std list somewhere with some elements of 8 bytes, 1 counter per element, even if it's a double, you will have a lot of memory lost compared to having an array. For the cache. Coming back to the cache. What mistakes we made for most of the implementation we have done today, this week except with the blocking, with the Grace code simulation. Let's say you have a big array you want to compute on, okay? 10 megabytes, for example. You access the first part of the array, okay, by making A plus B, for example. I say 20, but the first part of your array fit in the cache, so it fetch in the cache. Okay, you start to make A plus, for example. We increment the table here, for example. I am incrementing the first element, so it's in the cache. I'm incrementing the second one, it fetches the element, it's in the cache, so I increment it in the cache, etc. I progress. Next, I need to increment the next one. What is happening? I replace in the cache part of the, by looping over all the array, it will replace all the elements in the cache, because it will replace them while I'm accessing them. And then I continue. And if I loop again, what is happening? I came back to the beginning, but now the range part is not anymore in the cache. So I fetching in the cache, fetching from the memory. Okay, losing my time, and again loading from the cache. Exactly why the cache blocking is interesting, because if I'm making the cache blocking, I try to make everything done in my cache while the data is in the cache, and then I move to something else. And this is why I'm efficient in the cache. Yeah, I had several animations, sorry. So you understand why the cache blocking is so useful in practice? That's clear for everyone, thanks to this. Here I didn't discuss how I allocate the cache lines in the cache. Currently I considered I just replace one by one. This is not exactly the case, I will show later. Now I am running, for example, 6 threads on this architecture, which is a bit strange. You remember I spoke about this laptop hierarchy, where you have some fast cores and some slow cores. So there is a tons of questions which start to arise how to run on this kind of thing. If you have 6 threads to schedule on this machine, how you schedule them? Packed or not packed? Which I mean, how I schedule them all together on the same on the fast cores? Sorry, that way or that way? What is the best? Any idea? Huh? This one, for some reason. If I'm here, what is happening between 2 of the threads? Where is my pointer? Those 2 threads. What is happening to them if they are on the same core? Yes, they share the L1 cache. So each one has kind of half of the cache for himself. Okay? So if my application is memory bandwidth limited, because it's using a lot of memory, and if those threads are not communicating together, if they work in their side without discussing on different parts of the data, maybe it's better to put them that way, because they get a bigger L1 cache for themselves. Okay? Now, if they discuss together all the time, the threads are making some mutex to discuss, to exchange some data every free loops event. Is it better that way or that way? This one, yeah. Why? Because in practice, when you are communicating between two threads, you are communicating from you are communicating through the memory. So writing in a variable most of the time, and you write an element from a variable in one thread, and the other thread is reading it. Okay. What the CPU is doing in that case? If I'm here, this one posts a value in one variable in one variable. So the variable is in the CL1 cache. Okay. This thread here wants to access it. What it is doing? Yeah, it has to go in the cache hierarchy, pass by here, and get it from here. In practice, it didn't get it here. It invalidates the cache here, removes the copy which are here, and takes the hand on the copy. And if they are exchanging some message all the time, this is making ping pong between both. Very slow. If they discuss a lot, you need to pack them. If you are dependent on the memory bandwidth, you need to spread them as most as possible. Okay? This you can do in OpenMP. When you are saying OpenMP num threads, as this you probably know, the number of threads OpenMP is using, you can say, I want them to be close, packed. Or I want them to be spread, distributed over the cores. And it can depend on your application. If your application is bandwidth limited, fine to spread. If it's communicating a lot, then better to, or sharing the same data a lot, same to, good to pack them. You notice here I made a kind of HWlog bind core column 0 to 5. This is because when you say spread, if you say spread in an architecture like this, it will spread over all the cores. So some will be here and some will be on the slow cores, which in terms of performance, then I don't understand anything. Huh? It could be good to run in that case, but to understand the performance, it starts to become a bit mindful, difficult. So HWlog, this is one of the commands most of the people know in HPC. This is to bind the process, and you can say core, NUMA, socket, and giving some numbers here with a list, or a list with commas if you want just a few, to say where you want to bind those your threads. Okay. So if you are making parallelism, think about how you are distributing your thread on the machine, because this is important. You can also say you fill the machine. Well, in this case, you have no question. You fill the machine, it's good. But if you use less threads than the number of machines, the question of the topology is really important for the performance of your application. There was a question also during the week. Are we far from the performance we can reach? Far from the limit. So you remember that I spoke that in, the question, how I am optimal on the processor about the memory bandwidth and accesses. What are the limitations? And the answer, which is possible, it's the roofline model, which I shortly presented you. It was during the profiling course on Tuesday. And what are the constraints we want to measure in practice? There is two main resources you have in your CPU. If you want to look on the performance on the CPU part itself. On one side, the computation, how many floats I'm computing at a time. Why I don't have my pointer here? Okay, I lose my red point. One side is the number of floating points operation you are making per cycles, and one side is the memory bandwidth you are using. Two aspects of the problem. There is more, but we can focus on those two ones. Ideally, you can dream that you make such that your program is top at the both, at the two. So we can make a plot to see where we are on each of the domain in a single plot, which is what we call the roofline, because we put some roofs. So here we print the arithmetic intensity, so the number of floats, the number of floating point operation per byte. For 1 byte, I'm making 3 floating point operation, for example. And on the top, I'm putting the flops per second, so the top performance in terms of floating point operations, the compute performance. So here I have kind of, where is my pointer? Here I have kind of the performance in terms of full compute. And here I'm taking a grunt about the memory effects, kind of, the intensity. Then you can plot the limits. If you plot the limits, you have a first limit, which is the number of flops you can do per second, the number of floating point operation you can do on your processor at best. And you can put a limit, the memory bandwidth. If you are limited by the bandwidth of your L1 cache, your L2 free cache, etc., you are on this line in practice. So now your point can be on two sides. Either it's here and hitting the roof here because it cannot go higher due to the memory bandwidth. So it's memory bound. Either you're on the right and hitting the peak performance of your CPU, so you are compute bound. Okay. The good point of advisor, which I presented you during the profiling day, is that you can plot your points that way with Intel Advisor. You get the points with some colors depending on if it's a hotspot or not, and all the CPU lines. The scalar one, if you are not vectorized, where you should be. If you are vectorized, and if you are using FMA, where you are. That's the top limit of the CPU, okay, horizontally. And then in diagonal, you get the memory, the L3 cache limit, the L2 cache limit, and the L1 cache limit. So you can kind of know roughly, this is not a perfect measurement way, but get an idea of where your code lands, your loop ends in this graph. So during this week, I tried to make you a lot of optimization, speaking about cache blocking and pyramid, you remember? And the original version of Grayscott, which you have the naive version vectorized, but in a single way without blocking anything, is a triangle here. So I'm kind of relatively efficient in terms of vectorization, etc. But I'm limited in terms of memory because I don't hit the L1 limits, which are here. Okay, the limit, normally I should be able to go at the speed of the L1, which is probably here, ideally, in the best way. By making the cache blocking, just the rectangles, rectangles, I become the square elements because I'm already a bit better in the L1 cache, but not good in the L3 cache. Okay, if you remember, where is my pointer? So by making the cache blocking, I moved my code, the full application, from here to here, a bit better performance. And by making the pyramid, as I was using the cache a bit more efficiently, I was moving again up, okay, going to the root point. We see there is still some margins, probably, either on the vectorization side or on the cache usage. But remember that we have a case which is using a lot of memory for a few computation in practice. So I'm not really sure we can go higher in practice, or not at least with a lot of efforts. So we are already hitting the double precision vector limit, 84 gigaflop per second, which is already quite nice with the vectorization we have. And I don't think we have some FMA, so we are not able to reach this point in what we are doing. So that's to answer a bit the question, how I know if I'm far away from the limit. So don't expect to be on the top. To be here, the only way is to make matrix multiplication on a CPU. If you don't do matrix multiplication with the MKL, you are most of the time below. But it can give some hints on what you can improve probably on your code. NUMA aspects. I will be a bit fast because I already discussed a lot just yesterday. No, yesterday. Yeah. So this I already kept the chart. So you remember NUMA, you have several memories attached to every CPU, and if you want to access a remote memory, you pass by the link remotely. I remember that on current CPUs, most of the CPUs today, the big one on servers has NUMA inside the CPU, so you are not avoiding the problem most of the time. And I wanted to add something I forgot to tell you yesterday. If you have a program which is MPI plus threads, MPI plus OpenMP, try to use your MPI splitting in a way that you are not putting the threads over outside of the NUMA domain. So try to make such a way that every MPI process is running on one NUMA domain, so you avoid the problem. So yesterday I forgot to say one thing. The better way to use the NUMA is to avoid it. Go away of the NUMA if you can. This is better and simpler. And only face it if you are forced to do it. So you remember I spoke a bit about pagination. So I will enter in more detail now how the operating system is handling the memory in terms of pages. Okay, we'll open a bit the roof and see how it's working. So you remember that you have the application. This is you. And the thing you know about the memory up to now mostly is what is doing malloc and free. These are the functions you know. What is below, probably you don't know too much. mmap, munmap, and mremap. This is what malloc and free are using to ask some memory to the operating system directly. Yourself, you are not calling them directly most of the time, except if you want to do some optimized stuff. But between the hardware and the application, for the memory management point of view, there is an operating system. So you can say, oh, but the operating system has mmap and munmap. Why we don't use it directly? We can ask the memory directly to the operating system and not using malloc in between. Why having a memory allocator for that? The malloc infrastructure is there for one thing, is that in the mmap domain, it's handling only the pages. The pages I was speaking about, which is 4 kilobytes by default. And you cannot ask less than 4 kilobytes to the operating system. Of course, you, in your application, you want to ask for 16 kilobytes, 16 bytes probably, or 10 kilobytes, something small. You don't want to handle by yourself the fact that you need to ask a multiple of 4K for every allocation and probably split one page in something smaller. This is the goal of malloc, to do that for you. So this is why malloc is there in practice. So the API of malloc you know already. Malloc, you give a size. You have realloc where you give the pointer you receive in malloc. You change the size, giving a new one. And at the end, you free. And in C++, new your type and the size of the array you want to allocate and delete. Simple. Simple, but below, less simple. So I remember one thing. I remember that you have two memory space in practice in the operating system. I already said yesterday, but I will say again in more depth today. So one way is the physical memory, the addresses in the RAM itself, the physical addresses, and the virtual addresses of your application. The space, there is two things interesting here. The virtual space, you have some addresses which are going max to the size of your memory on the system. Okay, for example, 16 gigabytes on your laptop. The virtual memory space has one big advantage, is that it's a 64-bit space. So in practice, in hardware, they encoded really 57 now, which makes the virtual space very big, 128 petabytes. On some processors a bit older, this was 256 terabytes because they use less bits, 48. To encode the virtual addresses only. The other bits were just ignored because they did not consider it was useful to handle such a large space fully. There is one interest here, already, one gain about that. It's a bit like, you know, your student flat. You remember when some are still students here. Your student flat, when you came back on Monday from your family with your bags, you put your bags in your flat and then sooner or later, there is not any more places in your flat because you don't know how to pass around your luggage. Making the virtual memory management, this is a bit the same way. When your memory is full, if you allocate 15 gigabytes over 16, there is less room to know how to place the luggage. In the virtual space, it's like if your mind, you consider that you are living in a castle, even if you are physically in your student flat, okay? But in your castle, the luggage, you can put them everywhere. Okay, so the life is simpler for the memory allocator. It can place the element you are asking anywhere, as soon as, at the end, we can match the mapping with the physical memory. Okay, so I cannot put more elements than what I can put in the physical memory. But in terms of where I place my luggage, I can place them everywhere. The only thing is that between the physical space and the virtual one, the luggage will be split in 4K pages, in elements, and part of the luggage will be on one side, and part of the luggage will be on the other side. Same idea for the computer. Castle and student flat, you can remember. There is one interesting thing also, is that in the virtual memory, you are seeing only the memory which is accessible to your application. If Firefox is running there, do we have an image here? No. If Firefox is living there, with the credit card number in Firefox, your program by yourself and Grace Scott is not able to access the memory of Firefox because it's living in another virtual memory space. And both are not matching, not seeing the physical part which are to the other one. Okay? So this is one of the main concepts for the isolation of the processes. Also, you cannot access to the memory of the kernel. When you access to all the memory, if you scan all the memory of your program, you never see the memory of the operating system of Linux because of the virtual space. Because in the virtual space, Linux is mapping only the pages you required. The rest, you don't see. So this is a very old concept, which dates from 1962 with the Atlas computer. This is where they introduced this semantic. And in practice, the mmap and mmap call, I will succeed to say it. What they are doing is just requesting, when you request some memory to the operating system, is just saying, I want 1 megabyte of memory. So the operating system will say, I give you 1 megabyte here where you are allowed to access. If you access a memory which is here in gray, what is happening? You know it in C++, seg fault. You know this word you ate at possible when you are making C. This is when you are accessing one element outside of the mmap segments, which are allowed, the VMA, virtual memory address space. When you are accessing here, seg fault. If I'm accessing here on a page, I access to the data physically present remotely. And if I'm accessing to a page which is not mapped, because I said at the beginning it's virtual fully, there is a page fault. So a notification to the operating system to say, this guy is trying to access to a memory which is not mapped. The operating system would check. Either you are in the gray part and you get a seg fault, either it maps you a page to get a physical access. Okay? And malloc is here to hide you this kind of representation. So in malloc, you don't care about those pages. You say, I want this size, and malloc is responsible of asking the pages to the system, the segment, and handling for you everything about those details. If you want to understand why making a malloc is something not so simple. The origin of the concept of the memory management side, just for making some histories, is interesting sometimes to look from where the concepts are coming. This is a concept which dates from far before. I said this was the Atlas computer in '62, but the idea dates from 1956. This is Fritz Rudolf Gunst, who wrote a paper about saving some data on, how to say in English, on rotating tambours. To store the old way to store the data in practice, physically, just after the war. And he was thinking about these virtual addresses to save to ease the storage system he was building. So this is a concept which is very old. You can take there is a very nice anecdote article about this. I will not go through it. Stored at the IEEE Annuals of History of Computing. You can look on it. The article is 1 page. You can get some ideas on why you get this idea. This is interesting for fun. So I said there is a very big space. You remember this space of 128 petabytes. So how I store the addresses. I need at some point a table. I need a table which remember how I establish those links, of course. By the way, who is making the translation? When I access, me in my program, I wrote address 00x FFFFF8 in virtual, so an address which is here. Who is responsible of translating the address to the physical part, so the processor can access to the physical part? The MMU, yeah, which is where? In the CPU, yeah. In the CPU or in software. Originally, it has been in software. So every time you were accessing to an address, the operating system were called, should translate the address, giving it to the processor, and the processor should access it. Of course, it's very slow if you do it in software. So now it's encoded fully in hardware. So in hardware, they make the translation for you. So the kernel, the Linux kernel, is just responsible of building a table, giving it to the processor, so the processor can translate all the elements from physical to address, from virtual to physical. This table, of course, it cannot be a linear table. If I have a linear table to store 128 petabytes of addresses, I would have for every process a table of I don't know which size. I put it here. If you put a linear table, you would have 256 megabytes of memory to address all the memory of every process. Not very efficient, especially in a machine. This concept dates from a long time, so we didn't add terabytes of memory at the beginning, which we have now. So they think about hierarchical levels. So the first 12 bits, they take the virtual address, take part of the virtual address, and every part is giving an entry point in a directory. This is a tree in some point. There is the page global directory. When you access, you take the first 9 bits to know the index of this directory. Go to the next one, go to the next one, and go to the next one. Up to the end, you get access to the page address. Okay. So there is a walk to do about that. You walk about inside the page table. We call that. We call that the page table, and we walk about it all the time. This walk is done in the processor. Every time you access to an element, it has to walk over the table to get the physical address. But of course, it is not efficient to walk all the time. If you access, you have a loop on the same element all the time. Do you need to translate it all the time? If you access the same element several times, probably you can cache the address solving somewhere. Nice. This is exactly what they did. In most processors today, you have what we call a TLB, translation look-aside buffer, which is a small cache which is storing the address translation for the last, I don't have the number in my head, I forgot, 256 elements or something like this. It is very small, this cache. So in practice, 1,000 entries, sorry, I have it here. You have 1,000 entries in the TLB on most processors today. I don't know the recent one because I didn't check since 2 years, so probably they grew it, but I'm not sure. 128 entries, and one entry is addressing 4 kilobytes of memory on one page. 1,000 times 4K, 4 megabytes. It's not a lot, no? My cache is now 16 megabytes for the L3, 256 kilobytes for the L2. But for the L3, this is smaller than the L3. Okay? So at some point, they did one thing. This was introduced by Intel, if I remember. I don't know if it's the first to do that, but historically, at Intel, on x86, Intel has made it a bit before the others. It's what they call the huge pages. So to get a better addressing efficiency, instead of using pages of 4 kilobytes here, we were using some sizes of pages of 2 megabytes or 1 gigabyte. So with less entries in the TLB, you can address more. The thing is that we cannot put the 2 megabytes pages by default for all the system because it impacts all the IO system. And if you want to allocate one byte, you get 2 megabytes. This is not efficient. So we took a long time to make some implementation in the operating system to be able to handle a multiple size, I mean a mix of the size in your system. So when you need some 4K pages, you get 4K pages, and when you can use some 2 megabyte pages, you try to use 2 megabyte pages. This is what we call in FreeBSD. There is a nice paper about it in 2002 about a very nice implementation which they did in FreeBSD in practice to support this mixture of page sizes, which is called super pages. On Linux, it has waited 2011, 10 years to get the support of this feature. First, they get it with the old huge TLBFS, poor implementation, which was there also in 2002. But the transparent huge pages, which is something as native as the super pages, is 2011 in Linux. Myself, I was working on this kind of stuff, so this is a kind of topic I like a lot. So isolation, sorry, I have it here, I explained a bit before. For the isolation, this is exactly what I was saying. So with the pages, you can isolate the processes. Firefox, which is here, with your credit card number, because you put it on, I don't know which buying website, has access only to the red page, to the green page, and to the blue page. And GIMP, your drawing program aside, cannot access to the pages which are on the other side. Isolation. You can also make some shared memory. You know, probably you have heard about SHM, shared memory, which you can allocate on Linux sometimes. You can sometimes, if you really want, share some memory, so making the same mapping of the same memory between the two processes. Very efficient to communicate between two processes. You can just write to the memory, and the other one see it immediately. MPI, for example, is doing that. Questions? Thanks. Questions. Oh, a lot of questions. Alors, I will start from the beginning. Close separate CPU. Is like 2 threads on one core? I will skip this. Yeah, it's hyperfanic because it's answered. What kind of laptop have this so fast core CPU? This was a Dell XPS I had. This is the Core i9, the Core i9 CPU, which has this kind of to balance strange hierarchy. The first time I received this laptop for my work, I didn't notice that, so I was making some measurement and say, well, I don't understand the performance. I mean, it's very strange. It's very varying below my run. And at some point, I make ls topo to see the hierarchy and see, yeah, but this is totally unbalanced, also in terms of hierarchy. So look on what you are running on. Sometimes there is some very nice things to see. Yeah, Vincent, thanks Vincent, you had answered to Joseph. Some laptops with ARM CPU also, yes, ARM. Your phone, for example, has this kind of CPU. Your phone has some slow core and fast core since a long time, before the laptop. Is the TLB what limits how much RAM the laptop can have? No, not the TLB, no. The TLB is just a limit about the speed of the translation, not the limit of what you can address. This is just a cache of translation. So of course, if you access a page which is not in the TLB, you flush an entry of the TLB, make the new address inside of the other page you are accessing, and you continue. This is just that you pay a price. I will show you a chart after that. Yes, there is a question here. Good question. I will answer later. Keep it in mind. This is very important. Not a negligible thing. The operating system also historically has made this shared mapping at some point, which was leading to this, this Spectre attack which were done, where because the operating system were mapping also those memory in a protected way, so only the operating system can access this part of the memory. If your process will try to access it, it was not allowed. But when you jump in the operating system, instead of changing the page table to change and flushing the TLB, you can use the operating system can use what is at the end of the space. Sorry, I don't have my pointer. Why? I don't know why. It's not efficient to show. I don't know. The operating system at some point is mapping itself at the end of the process with a lock, saying that only the operating system can access this part, thanks to the ring it is in, if you know the ring theory about the operating system. I will not enter in it here. Just to show some examples, you will see what I try to show here is that this page the description, this virtual memory, is allowing a lot of things in practice with a single idea. Isolation, performance, I will show some other stuff. Lazy page allocation. So this is what I explained yesterday. At the beginning, the page is virtual, and when you are making the first access, you get the physical page per page. Of course, if your threads are not on the same NUMA node, they get pinned to the right NUMA node at the first touch. And we call this lazy page allocation or first touch for the semantic in the operating system world. This I already discussed yesterday, but now you understand a bit better how it is behaving, probably. But now we can look, there was a question about the cache. How the cache is allocating where it's placing, I mean, which line it will evict when we will access an element which is not in the cache. We need to remove an old one. Which one we decide to remove? In practice, most of the caches are running with what we call the cache associativity. Cache associativity is what? Let's say I access to this element in green. How do I know where it is in the cache? Either I have an index on every line to remember which element of the physical address it's caching, and I need to ask, are you on the first line? No, I'm not on the first line. Are you on the second line? No, I'm not on the second line. Are you on the third line, etc. And I check all the cache line by line to know if the data is in the cache. This is not efficient. If the cache is big, 1 megabyte, you don't want to check element per element. So what they did is to split the cache with some colors, kind of, what we call ways and lines. One way is colored with all the colors, part per part, and there is 2 ways colored to the same way, to the same pattern. Now, what the cache is saying is that if you are accessing a cache line, 8 bytes, you remember, the 64 bytes. If you are accessing a part which is in green, it should be in the cache only here or here, on a 2-way cache. So now, if I am accessing a data, I just have two locations to check. First location, second location, it's there or not. If it's not, I need to ask to the cache on top. If I need to ask on the cache on top, of course, I will evict one of the data, will select one of the 2, remove the data which is inside, and put the new one. This is how it is allocated for the question which was asked in the past. Now there is a problem in this. If I'm accessing an element which is green, jumping to another element which is green, both are entering the cache. And if I access again to another green, it evicts one of the elements. And if I'm looping over this green, 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 I'm not benefiting of the size of the cache because I have only 2 elements which can fit in the cache instead of 3, where normally it should go with the size of the cache. Okay? So if you jump far away with some multiples in the memory, you finish to have some problem. There is some kind of resonance which can arise due to the cache hierarchy, the way the cache is running internally. I will show you some example. But this is even a bit worse. This is even a bit worse because you remember there is a virtual memory on top. So here it's joining the question which was there, is the cache using the physical address or the virtual one? What do you think? Yeah. So this is physical one for the L1 and the L2, and virtual one for the, no, physical one for the L1, sorry, and a virtual one for the L2 and the L3, depending on the cache hierarchy. Because the L1 need to be very fast. You cannot get the translation of the addresses in the L1, otherwise you lose the performance. The L2 and the L3 are slower, so you can use the virtual addresses inside. So there is this scheme in practice. You have the virtual pages on top. But what if my operating system, you remember when I ask a page, it will give me one page when I will access it, but a bit randomly. We will see the algorithm exactly which is used in the operating system, but if I'm not lucky, I can find in some troubles. If the operating system is giving me a red page, a green page, a red page, and 2 green pages, and if I'm looping on my array, what is happening? Yeah? Conflicts. Conflicts because the first element of my array will fit in the cache, second also, third also, but the fourth not. And I will start to lose some performance. This is historically a problem we have on Linux because Linux is randomly choosing the pages. When you ask a page, it's looking in a list and taking the first one and giving it to you. So it can be, if you are not lucky, all the same color. And you can measure it. This is the kind of measurement you can do. Here I have the size of the cache and the number of conflicts in excess due to this problem. And the L3 cache in practice is so big that statistically you can have exactly this problem. So in gray, this is a measurement, so it's varying depending on the randomness of the thing. And in black, this is a simulation considering a real random system, fully random. Not because the real one is not exactly random. As it's taking the first available in the list, it's random roughly. But we see that we have a kind of leak in the cache. The cache become less efficient before the end of the cache. So yeah, you might heard sometimes some people are saying, yeah, but you should use a table which is a bit smaller, a buffer which is a bit smaller than the cache, and not exactly the size of the cache. Okay? So most of the people considered historically that it was due to the fact that some other processes are running aside and polluting the cache. No, this is on Linux, this is a mistake of the operating system. And it's still today, in some ways. We can use the huge pages. The huge pages don't have the problem because the huge pages, they cover, one huge page is covering one way totally because it's big enough. So a huge page has all the time the same color inside, green, yellow, blue, red, green, yellow, blue, red. So it doesn't, they are all colored the same way in some ways. They all have all the colors, so they are efficient. And you see, for example, this is an old processor. This is a bit old, this problem. I will show that today it has improved. In blue, using the huge pages, the efficiency of the benchmark I have discussed before about the cache measurement. So in blue, I see the L2 cache, the L3 cache. And when I am at the end of the L3 cache, a bit before the end, I'm going up. If I'm using Linux with the 4K pages, the randomness allocation, the random allocations, after 4 megabytes, losing performance. Half of the cache. I pay a high price for the cache. Half of the performance. And you see a small bump here. You see this bump? TLB. This is the TLB effect. After 2 megabytes. Normally it's after 4, but the way I'm using 2 tables here in this measurement. You see the TLB effect here. So the TLB is not, except if you're making some random access. If you jump everywhere in the memory, the TLB, you start to see it and you start to penalize your application because you never use the TLB by jumping everywhere all the time. If you are using linear access, most of the time, the prefetcher, etc., succeed to hide the TLB effect most of the time. So it's not a big impact, the TLB on numerical simulation, most of the time, this is not a problem. This is a problem for compilers or, everything which is managing trees in practice. Yes, the huge page, as I'm saying, it's managing, covering all the way. How many ways do I have on a processor? Here I say 2. Any idea? On the number which is in real life? Most of the time it is 8, 16, something like this. You have 16 ways in practice in the cache, which means that you can access 16 elements colored the same way in parallel, I mean, at the same time in the cache. This is not a lot. I will show the problem later. Yes, this is theoretical thing I will skip. So for the coloring, I said there is two ways to it. Yes, there is one way to avoid it. This is the huge pages, because the huge page is covering all the colors in one go, because it's big enough. OpenSolaris also has there is free operating system available today, mostly free for the open source one. FreeBSD and OpenSolaris, both are using huge pages sometimes in their implementation. But you can also do something which is coloring, page coloring. FreeBSD and OpenSolaris are doing it also. Instead of giving you a random page, they take care of the color of the page which is assigned to you depending on its location in the virtual space. So I try to balance the colors over your segment. So we can say, I have three systems, one with 4K random pages, Linux, one which is operating system, which is OpenSolaris with page coloring, and FreeBSD, which has this huge page implementation natively supported. Is Linux slower due to random paging? What do you think? Linux is wrong? Yes or no? Who guess? Yeah? I have a yes here. That's what I guessed during my PhD, and we searched a lot, and the answer is, we will see, no. So I will present here some results on an old processor because I didn't make again all the charts I will present, but you can do the same kind of thing on recent processors in some ways, even if the problem has change of scale, it's less present today. I take an old processor, an ALM. This is a bsocket workstation. I try to change the operating system. So if you change the operating system, most of the time you change the compiler, the MPI implementation, the binutils, the BLAS, etc. You change everything. So I try to fix everything, compile myself everything except the operating system. And I say I will compare an application on all those three systems just to check. So I'll take a numerical simulation, which was a LRMHD at CEA, something done by a PhD student, doing a bit like, in terms of accesses, in terms of memory accesses, what we do in Gray Scott in some ways, no cache blocking. And I have this chart. Linux in red and green, depending on if I'm enabling the huge pages or not, is fast. And FreeBSD, which has the huge pages, so normally the correct thing is slow. And OpenSolaris, which has the page coloring, is relatively as fast as Linux. But FreeBSD was supposed to have the best implementation, and it is the slowest of all. And when I was searching, at some point, I found that I say myself, yeah, but maybe there is a problem with the I/O part of the application, something the operating system can impact. But I searched a lot, and I finished to find that the part of the code which was slower was this loop. For a loop over a size, and I made x1 equal x2 plus x3 plus 1 plus x9, 9 arrays. Oh. I make a loop, I change the operating system, and one is 1/3 slower. Strange, no? I don't expect that. So what did I change? I changed the user space malloc function because each operating system is providing its own malloc. It is not the same on each system. The paging policy is changing. Of course, this is what I want to test. The scheduler is changing. So I say to myself, OK, I pin the thread, so no, the scheduler is not involved. Same problem. We can change the allocator. So I try to make a small memory allocator with the same kind of pattern allocated for this application all the time, independently of the operating system normally. And I get this. Now Linux in red with 4K pages is fine. Linux with huge pages is not fine, as FreeBSD before. FreeBSD is fine. Oh. OpenSolaris is not fine. But come on. I change the allocator, I change the operating system, and my loop is becoming slower. What is the difference when you change the allocator? What it changed? The only thing which is different is the address it's assigning to you, the virtual address. Okay? So the virtual address, normally it changes nothing. If I shift the segment in the memory, normally I expect the same performance. Yeah, but if I have 3 arrays, let's take a cache which has 2 ways to simplify the view. One array is allocated with 2 megabytes. Another array is allocated with 2 megabytes. Another one is 2 megabytes. If I'm unlucky, the operating system can align the segment I'm allocating on the huge pages. A huge page, it's efficient only if I'm starting from the beginning in terms of memory management. So I try to align to 2 megabytes. Yeah, but now, what is happening to me? First element of the page is necessarily green. Second element is yellow. On the other array, my second array, first element is green, second element is yellow. And on my third array, same thing. Now I'm making A plus B plus C in loop. A plus B, they go in the cache, plus C, throw away one of the elements of the cache. And I kill my cache. So the choice of the addresses has some impact on your performance, where you didn't think about it. This is something we suppose it has no impact. So here the problem is because OpenSolaris, when it makes its page coloring, they made it in a regular way, what I call, because they allocate all the time the pages in the same order: green, yellow, green, yellow, green, yellow, green, yellow. I mean, green, yellow, blue, blue, red, green, yellow, blue, red, green, yellow, blue, red. If you random a bit the pages, which Linux is doing, you remember Linux is doing random. If I'm making random, anyway, I get different colors at the beginning of all my segments. So I'm fine. So Linus Torvald, everyone was saying to Linus Torvald about this memory management, you should do page coloring, you should do huge pages. And every time he was saying, no, but this is the HPC guy who don't want a memory management layer. In practice, we want this. And in practice, this will be a big problem for the rest of the system. And he never wanted it for a long time. And he still don't want it. Huge pages, it's there. But page coloring is still not there. But in some ways, for the common applications and to be efficient on everything, it's better. Because what I'm losing here is a factor a lot. When I'm efficient, I'm more efficient, but when I'm losing something, I'm losing a lot, when I'm falling in the gap. It's catastrophic memory accesses, kind of, to cite my colleague. So what to do? How you can improve the thing? If the memory allocator don't try to align, just shift a bit the thing. What I made here, sorry. Yeah, I have this here before. Yeah. Just to get some numbers. Here we have, for example, one processor which has an L1 cache of 48 kilobytes. Instead of 32, this is what you can get sometimes. You can have 12 associativity of 12 for the L1, associativity of 10 for the L2, associativity of 12 for the L3. Of course, it depends on your processor, and now the numbers tend to increase. Okay, so it means that here in a loop, I can use at most 12 arrays at the same time if I misalign them. Remember the problem I was saying here? It was 9, and at that time the processor was an associativity of 8. 8 compared to 9. I have one element which posed problem. One array which was posing problem. How I can fix? If I have a system which is making a regular coloring, how I can fix the problem? I just shift a bit one of the array in memory, in the virtual space. If I shift a bit the third one of a few pages, now the first page of the element is blue and red. Now it's using the cache efficiently. So when you see some people, depending on the system, if you want to use the huge pages of Linux, and you want to fully align. Now, some people are saying, for the vectorization, I will use a POSIX memo line. Never put a very high value for the alignment. Put a small value. If you put a big value, you will finish in this kind of problem. Me, I fall in this problem because OpenSolaris, when you do an mmap was aligning by default to use huge pages efficiently. FreeBSD was also doing that. And they were all aligning at the allocator level at 2 megabytes alignment, which is a mistake of the allocator. But it was impacting the application. But it's a mistake of the system. You should not have to take care about this. This is a mistake of the developer of the operating system. So if ever you do a memory allocator by yourself, avoid to align too much the thing. Let some random shifting inside the blocks you are allocating. This is better. The slowdown was even worse because if you use multiple threads on the same core, the L3 cache is shared, but is stressed a lot. So then the performance can be far worse. Here I was able to get up to 3 times the execution time on FreeBSD just by using threads, falling in this issue. If you shift, so here there is a chart depending on the gap. So if you aligned or not. So here, if you have an alignment multiple of the problem size or random size, not a random size, but the size multiple, depending on the number of arrays you are using, you see that if you align, you have some troubles quickly. If you misalign, if you don't align, you can use 60 arrays in your loop. There is no problem. Okay. So try to take care if you align too much the thing. This is not a good idea. Not at all. So I'm speaking of a problem which has disappeared a bit now because L3 cache now is protected against this problem because the cache is now built with some hashing addresses. They hash the addresses instead of having something regular. So they can random a bit how they are placed in the cache. So the L3 cache is now partly protected against this problem. But the problem is still present on the L1 and the L2. So if you don't take care, you can kill your cache efficiency in the L1 and the L2 due to this kind of issues. So I made here a measurement on a more recent processor. You have this. Instead of having, you remember, I had a big ramp up at the middle of the cache. Now you see we still see an effect a bit, but which is slower and going far away. So if you make some measurement on cache today, you don't see a big plate ramping up and a long plate. You see something going up a bit slowly up to the end, which is now not due anymore to the page system, but due to the choice of the hashing address system that the CPU is using itself. So this kind of hashing is done for AMD Zen architecture, Intel one also. IBM was not doing it on Power 8. I don't know Power 9, and I don't know for the recent one. I didn't check. ARM V8, V7, and V8 were not doing it, so you had the problem. The more recent architecture of ARM, I don't know if they finally fixed the thing the same way than Intel and AMD. But just to understand that sometimes, depending on how you access your elements, there is some side effects you can see in your code. So L2 and L1, if you are fitting in the L2 and L1, you need to check that your access are not falling in this kind of problem, because possibly it can make you losing the cache where you try to use it. Another problem, 4K aliasing. You take this loop here. AI might equal BI minus 1. I shift one element left. If you look on the address, modulo 4K page, you will think that there are different addresses, but in practice, the CPU, to be faster, the Intel CPU, AMD is not doing that too much, but it depends on the CPUs. In the cache, when you access two elements, no, not in the cache, sorry. You remember that I said that you can schedule several instructions at the same time. to parallelize a bit the instructions. If two instructions are accessing the same element, can I schedule them in parallel? No, because if they access the same element, I will make a mistake. So the scheduler of the CPU has to understand that two instructions are not accessing the same address, to check the address. But of course, they have to be fast in the decision. The instructions are going fastly on the CPU to not slow down the execution. So what most of the processors are doing is that they are not checking all the bits of the address, but just a part of the bits, which means that it makes some kind of modulo. So if ever you align too much the pages, you align your arrays on the pages limits, 4K, making 4K between two elements, this loop will be not performant because only a part of the address will be compared, and so the CPU will understand more oftenly that your instructions are accessing the same address. On an old CPU, the gap was very big. Now it has been tempered a lot. Now the gap is a bit smaller. There is a benchmark in the memory container to measure it on your processor. You will see that it's far smaller today than it was in the past. But it's still there a bit, a few 10%, something like this. Again, you shift a bit your array of a few elements, you gain the performance. So again, aligning on the beginning of the page all the arrays is not a good idea. So when you are doing POSIX memoline on 4K, again, bad idea. Bad idea for the memory allocator also, because for most of the large arrays, they are doing that by default. At least the Linux one is doing that by default. If you allocate 1 megabyte of memory, all the arrays will be aligned same thing on the beginning of the page. So by default on Linux, you fall on the problem. So if you are doing some A equal B minus 1, shift a bit the array. You will win 10% of performance. I don't know what is the time. I have 30 minutes. Will I go through this or not? Yeah, we'll probably. Yeah, we'll go through this. You remember the application I was speaking about with a big gap of performance by changing the memory allocator? So this was this kind of numerical simulation, so multiphysics with fluids, etc., with a mesh refinement. And at some point, it was doing a lot of big memory allocation all the time. A lot. When I say a lot, this was millions. 70 million allocation in 5 minutes on 12 core. Stressing a lot the machine, a bit like Python in some ways. And it was with blocks of roughly 20 megabytes. So giving 20 megabytes to the system, taking 20 megabytes, giving 20 megabytes. Just to give you some hints about the performance about the system, if you want to change the memory allocator in your application, you can take one of the 4 ones which are here, gmalloc, tcmalloc, howard, or memalloc, and try to test it on your application. Sometimes it can improve the performance. And to change the memory allocator, you just compile it, and you need to LD preload it on your program, if ever you want to play. Sometimes you get some changes that way. So here there was a question. This is the performance on the NUMA node I was presenting at the beginning of the week during the profiling presentation. And there was a question, is it the case also on a simpler CPU than the complex one I was using? Yes, in this case, the gaps were smaller here. Because the machine was less stressed. It was a single CPU machine, no NUMA. And there it was passing in a better way. But for the physical memory, no. For the consumption was changing a lot. Time to discuss one thing. How you measure the cost of malloc? Measurement method. I start a clock, I do malloc, I stop the clock. You agree? Everyone agree with that? or you feel the no, but yes, if you do that, it depends. For the small block, yes, because you go to malloc. Malloc already has some cache memory, some buffers under his hand. The pages it has allocated before. It can take one element on this page and return it to you. So it's very fast. So normally, in this case, you pay only the price of malloc. So this is true. But for a large block, you remember what I said for a large block? It is virtual first. So when I say malloc 10 megabytes, malloc, I say to the system, allow me to access 10 megabytes somewhere, but I get no page. So when I return in malloc, I'm counting here only the time to be allowed to access to the memory, not the time to really access it. So if I had a memset or a loop, which is accessing it in addition to the measurement, normally for a large segment, the good way is clock, malloc, making a first access to first touch, physically getting the memory, clock end. And the numbers are quite good, quite huge. Huh? If you measure that way, the first measurement is saying you are measuring 0.08 million cycles, where the measurement with the second part taking in account the first touch is 1,200 million cycles. I missed a lot by making the first measurement. And that's one of the problems. For the memory management, many people say, yeah, but when I profile, I see that malloc is not costly in my program. Yeah, but you pay the price later when you make the first access. And this you didn't measure, because this is not a function call. So yeah. How the large blocks are managed in a memory allocator. Most of the memory allocator, when they want to allocate more than 256 kilobytes, most of them, what they do, they call mmap, and they give you the address of the mmap. All. And kind of tcmalloc is the only one making something different, but they all do that. So for all those allocators, you pay the price later when you make the first access. And when you make a free, they don't try to cache the large allocation, they return it to the system directly. So if you allocate 1 megabyte and return 1 megabyte, you exchange with the operating system. It's not cached in the application like the small blocks. Exactly the problem I was showing with Python before, in some ways. So just to speak about NUMA, here it's to speak a bit about the problem I was working during my PhD. So me, I said myself, yeah, the large blocks are not recycled by the malloc. So I will do a malloc which recycles the large blocks. For HPC applications, this is useful. But if you want to do this, you need to avoid the fragmentation on the large blocks, because you will have some holes on the large blocks, so losing a lot of memory in the holes you didn't occupy. You need to take care of the NUMA yourself. Now this is the allocator which is responsible of the NUMA if you do that. So you have some problems. And to limit the locks, because you want to be parallel, of course. So I made a memory allocator which has several profiles to run, either a low mem profile. I try to return the memory all the time to the operating system to not consume too much. A uniform memory access architecture profile which is not taking care of the NUMA, and a NUMA profile to take care of the NUMA, just to show how it impacts the application depending on the way we are doing. And this is exactly the chart I was presenting yesterday at the beginning of the week. If you take care of using the low memory profile, if you return too intensively the memory to the system, you are very slow. Me, I was very, very slow because I was very, very aggressive. Of course, I was able to temper a bit this if I want. But here, this is the worst case I present. If you try to keep the memory and not taking care of the NUMA, this is to explain if you are doing a memory allocator inside your application, you need to take care of this kind of stuff. If you make a kind of buffer to try to temper what is the system. Most of the applications, sometimes they say, I make a memory allocator in my code because I will be better than the operating system. Yes and no. If you don't take care, you already win 20% by keeping the memory in the system, but I'm not at the best because if I take care of the NUMA, I'm at factor 2 improvement. Again, on the machine with 16 NUMA nodes, so not the simple one with 2 CPU. So there is a question, why it is so slow to return the memory to the system? Normally, it is just assigning a page, no? It assigns a page, so changing a pointer in a page table, and it should not cost too much. Yes and no. If I want to measure the page fault time, I want to measure the time of a page fault. What I do a micro benchmark. I make an mmap to be sure it is not mapped. Okay, to guess virtual memory. I make a for loop. Where is my pointer? Here. I make a for loop and I make a time distribution to measure the time to access each pointer. And I get the time of the first touch all the time. And I get a chart like this. This is on a recent architecture. With 4K pages in sequential, I get something like this. And in parallel, I get something like this. Already, you see that in parallel, you are very slow to allocate the page, slower than in the sequential case. Because in sequential case, in average, we can say we are at 2,600 something. Here, in average, I'm at 6,000, 6 times slower, just to get the pages. Because I made a parallel OpenMP4 to make my measurement here. If I'm allocating an array and touching it in parallel, I'm slower than if I'm doing it in sequential. Why? This is, I don't care. So I studied this problem a lot, this scalability problem. So here you have the number of tasks which are touching the pages and the performance of the system to answer and to give you the pages. If you are using processes, one process, one thread. So they don't speak together, they are in a different virtual space, each other. It's scaling quite well. If I'm using one process on my machine and several threads, I'm going in the wall. With 128 threads, I'm 128 times slower. Not efficient at all, at least for the memory management part. This was even worse on the Intel KNL because everything was going in the wall very fastly. KNL we don't use anymore, but at that time it was a very big problem on this machine. We can say we can use the huge pages. You remember the huge pages? They are huge, so I get less pages in one segment to allocate my segment. If I have 4 megabytes, I have 2 pages to allocate instead of 2 megabytes for 4,000 something pages. Yes and no. It's not scaling again. Why? So I looked in the operating system at some point, and I opened the roof. And if you look in the operating system, when you have a page fault, what you need to do? You generate an interruption, and the processor is interrupting the operating system, saying, there is a page fault, check if it's legal. The operating system needs to lock the page table, of course, because no other thread needs to go in it. They check the reason of the fault. Is it legal or not? If it's a first touch, we need to make a lazy allocation, so we need to request a free page in the free NUMA list. Here, there is also a small lock. And we need to clear the content of the page. And then we update the page table and we release the lock. How much it costs, all of this? If you measure the cost of a page fault, roughly in average 1,400 cycles, 3,400 cycles, sorry, the number which is here. 40% of this cost is here, clearing the page, putting some zero in the memory. And because when you request a page from the operating system, this page can have been used by Firefox before and have your credit card number. So you don't want to give this number to the next process. So every time you request a page, there is a mem set which is done. When you touch a lot of pages, it starts to cost a lot. And in addition, you do it in the lock. Yeah?
Do we typically have garbage when using a new memory in a new area in the memory? if it's cleared?
Yeah, I will make a schema with some movement, so you will understand after that.
Okay.
So there is different approach to solve this problem. Microsoft, at 3 times, they are freeing the pages, making the 0. Microsoft, on Windows, they make the zeroing at 3 times. So when you are making the allocation, the first touch, you pay no price because it's done already. On Linux, this is done on the first touch time, so you need you pay a price, and you pay a high price because it's also in the critical section. Huh? So if you do it in parallel, you lose all the performance. So the question was for me during my PhD. I would just explain something to understand some feature of the system. I tried to make one optimization about this. So the first one, the good one, I think, is the way of Microsoft. For one time, Microsoft has made a very nice thing. I hope that at some point it will land in Linux to make the same thing. But during my PhD, I tried another way, is to say in HPC, anyway, making this memory clearing, even at the free time, is a loss of performance in HPC. So can we avoid to have it? So I say yes, because when you are doing HPC, most of the time, what you do malloc, initialization, so you don't need to initialize again the page all the time. So just to show the normal thing, the normal way is that process 0 has some data with your password or your credit card number. Okay, you free it. It goes in a free list in the operating system, stays there. And when another process is making a first touch, it gets the page. And if you don't clear the page, of course, the password is landing in the other process. Security issue, you don't want this, of course. So you are forced to clear the page. So just to say an interesting thing, during my PhD, I was adding a local pool to each process. So the pages will be able to exchange between those pools without being cleared because it's some pages from this application. And that way you can gain a lot of performance by not clearing the page all the time. Just to see the gaps which are there in performance. So I was forced to extend the map policy because sometimes you need some 0 because the application expects the pages to be 0. But just by using a map page reuse in a map, I was able to get the optimization. And in practice, sorry, where is the chart? Yeah, that's here. In red, this was the official kernel, and in blue, this is the optimization. Nice gain. Nice gain because it was a factor 6.8. And the even better gain was with the 2 mega pages. With the 2 megabyte pages, you have 2 megabytes to clear. That's a lot in practice in a call. There, I was able to gain a factor 660 in practice in terms of scalability. Quite well, huh? So I would say if we can remove totally the clearing of the page in the kernel, it should be good. This implementation is a bit complex in practice to do. But I hope that one day Linux will do the same thing than Windows to do it at free time, where it can do it with no locks and nothing critical on the system, on your application. This I will skip, so I will stop here for the presentation. Just consider the genius of the people who invented the pagination, because it solves a lot of problems in one single idea, even if it poses some problem of performance sometimes. And even if there was 60 years of memory management research, there is still a lot of problems to solve. We are still there today. And current operating systems still have to digest correctly the multi-core and NUMA architecture. There is a lot of effort to do on that, even today, even if it has progressed a lot. And the impact when you make a mistake can be huge. I have seen that all the time. This is some factor 2 or 20% of performance loss. So if you sum all of them, it starts to make some gain, which sometimes compensate totally what you can do with vectorization. So hope you know better that what is behind malloc now, to understand a bit how the memory is behaving and to know how much it can impact you. So I will stop here. If there is some questions, we can discuss more, and we can look on the small benchmark to execute them to see today where it is. Yeah, question online. Where there is some question on top, but oh, there is a lot of questions. I will start from the back. Int is not an object, but no, this is the answer from I don't know what. Oh, Joel is responding. So where is the first question I missed? It should be there. On a laptop, its physical size and power consumption are limits, I think. No, this is the TLB watch limit? No, I already answered. TLB should not be. No, new and delete, they are most of the time calling directly malloc. There is a question, is new and delete making something else than what malloc is doing? In practice, they kind of directly call malloc. Eventually store the size, the number of elements at the beginning to know how much they need to delete and to know the size to free. But they don't know anything else than that. And calling the constructor, of course, in addition. Joel already answered to most of the questions, so I will not take all of them. Joseph, what is this? I can zoom if everyone wants to see it. For me, huge page size is too. Oh yeah, the huge page size, the 1 GB page size is mostly never used. Some people are using it for databases sometimes, but in practice, in the systems, it's very hard to manage because you need to have no fragmentation to get them. Because to get to 1 GB page, you need to have 0 page of 4 kilobytes in the middle of it to be able to give it to the application. So there is a fragmentation problem to handle now. And the good point of the 4K pages is that there was no fragmentation because all the elements the kernel has to manage is 4 kilobytes. With the introduction of the two sizes, now there is again fragmentation to handle at the kernel level. And the 1 GB pages are a bit a problem. So in practice, the system is never using the 1 GB pages except if you ask it explicitly. Yeah?
Does the kernel sometimes try to defragment?
Yeah. There is a defragmenter inside. No, it's recent, but yes, there is a defragmenter to defragment the pages. Yeah. At the beginning, it was a big problem because there was no. So at the startup of the machine, you were able to access to allocate some 2 megabyte pages easily. And after 1 hour of run, or even half an hour by running a graphical interface, it was not possible anymore. This is what FreeBSD made well in their paper Super Pages. They make a very beautiful implementation about this, which require no defragmentation at the end. So this is very efficient on their way. I mean, no, not a lot. Joel is answering to a lot of questions. So if there is some questions here, no question? You are all memory experts now. So maybe we can run some benchmark just to see how it is today on a recent machine. So if you take my image about memory, there is in a 7 OS memory some benchmark, so we can go on it. Examples. 7 OS memory. I first have the example, the list versus vector. Yes, there is a question. Where is the microphone?
Yes. I don't know if we have time to ask questions, but I didn't understand the graph for cache associativity. When you split the L3 cache, why do we still have a curve
and not something flat? Is it because we still don't use huge pages? And is it still better than before? I'm not quite sure how to quantify.
This one?
Yes. Is this better than
This is
without
because
splitting?
in the recent L3 cache, they randomize the address placement. So they put a hashing function in practice to randomize the address. So kind of make a random coloring in hardware. So you avoid statistically all the problems I have described before in the L3 cache directly in terms of hardware. So kind of they can recognize that Linus was right to not want it the page coloring by making a random thing directly in hardware. So any operating system which was doing the coloring was doing the right thing.
Okay, and so follow-up, does that mean that Linux is now randomizing something already random?
But Linux is now not worse, not better than the others, because as the thing is random in the hardware level, making some random on top of it is just changing nothing.
And so is this better than the graph you showed before? I can't tell because I don't have them side by side.
So it's not better for one application if you optimize your application and taking care of this, because now you lose a bit of performance of your cache, a bit. But statistically, on all applications, if you use many arrays, etc., you don't fall on the problem I was describing before. So me, I was very happy because this was something I was proposing during my PhD to make this hashing function in hardware, and they made it. But they made it on their side, so this is not because of me. Any other questions before I move to the benchmark? Maybe online? What are the slices in AMD? The slice. Yeah, so the slice I'm speaking here is that the L3 cache has become so big that it's very hard to address it in one go, and it has access also by many cores. So if you have one single entry point to the cache accessed by many cores, it starts to cost a lot. So what they did in practice is to split the cache, the L3 cache in domains, in slices, what they call, and each slices is handling a part of the cache. So when the core want to communicate, it need to define to which slice the address will land on with the hashing function. This is where it arises. And then if you are on the cache one, the core one will go through a circular bus to go access to the cache, and the data will come back to the L1 cache. So it increases the communication bus in the cache hierarchy, but it permits to have kind of several L3 cache in one, unified in one cache in terms of visibility. That way they solve the scalability of the L3 cache, which was limited at some point. And this is where they introduce this hashing function to distribute the data over the several slices. This is why I'm saying I propose the hashing for the pages, and they made it to solve their problem of scalability in the cache. So they made it for their own reason on their side. And this is done now. AMD and Intel are using the same kind of structure now for the L3. I don't know the other processors. Is there some question online? Just to give you an idea. This is an answer of Joel. Maybe I can take some other questions. Just having L1 shared between all cores. I suppose it might be a lot in terms of memory management. The L1, you don't want to share it between cores because otherwise you will need to lock the cache depending on how the cores access, and you want a very fast cache. So no way to make it shared between the cores. No way to the L1 cache is answering in 2 cycles. 2 cycles is very fast for the processor, and you have no time to make anything. This is why there is no address translation or nothing. And this is also why it's very small. What is the benefit of having a laptop with a Core 7 compared to Core 5? Core 7 to Core 5, this is the number of cores you have physically, generally. And Core 5, you don't have hyperthreading most of the time on your cores also. to just show the core. Maybe I have a draw. Between the core E5 and the core not always, but most of the time, the core E5 has some cores like this without hyperthreads, and the core E7 has some cores with hyperthreads. If you in the Intel nomenclature, this is that way most of the time. Most of the time, because sometimes it's not that way. No, I have it here. So maybe I can go to the benchmark. So first example, one list versus vector. If I'm packing, you know, the problem of the line caches. List versus vector. I execute it. It's a bit long, this benchmark. So I measure in cycles here per element. List 100 free. To fill the list, of course, I need to make some mallocs, etc. So it takes a lot. 100 cycles to allocate. Where to increment? Increment, I'm making an access. Maybe I can show the code. This is exactly the code I had in my example. Up. I'm pushing some element on the list to fill the list, and then I'm just incrementing it with some doubles. Okay. To increment with the list, looping on the list to increment all the elements, and due to the randomness of the memory and the fact that I'm not rightly placed for the cache with the holes, which are useless. 6 cycles. Now I do the same with a vector, 2 cycles. List versus vector, this is the gap. A bit the same if you do array of struct or struct of array. This is exactly the same kind of thing you can see, depending on the size of the struct. Second example, cache accesses. This is to measure the. So I'm increasing. This is to make the chart. I use the chart with the bump, depending on the cache level. So I'm taking an array and increasing its size, and all the time measuring the time to access it in loop. So this is something difficult to measure, this thing, because with the prefetcher, etc., you need to stress enough the cache hierarchy to really see it happening. And I know that on this processor, I think I should have improved a bit my benchmark. I forgot to pipe it to something. No, I pipe it automatically? No, I didn't. No, I made the plot. Okay. So I'm increasing the size of my array and measuring all the time the access time. Here I'm measuring either the median or the average. The median is a bit more stable than the average because the average has the interruptions inside, which cost a lot. This is long. This is long because this processor has a 16 megabyte cache, so I need to go a lot. We have seen that now this is six cycles to access one element, where it was 2 before. 9, it's increasing, so we have maybe start to go to the memory. 10. What it says is that for the Grace Code school, if you are in the RAM, you are 10 times slower, 5 times slower than being in the L1 cache. That's a factor 5 speed up you can have on your hand, on this CPU. I come and reach the end. And I'm a bit sorry, I think the chart is not totally, I did not optimize to make this measurement, you need to optimize a bit the benchmark for the CPU you want to run on, have the right size, the right number of repetition, etc. And I don't tune it yet for this machine, but we can see what it gives. Can already plot a bit, maybe. New plot point new plot where I am. So we see we have at the beginning you are not efficient. If you are too small, the arrays, there is some other problems which are the time of the loop, so you don't measure anything useful. You have the L1 now. The L1 is very hard to measure today on the recent CPU because you need to stress a lot all the hierarchy to see it. So the L1, for example, with my benchmark, I don't see it here. The L2, which is here, 32 kilobytes. And then we'll see a bit the L3 arriving at some point. So maybe I will not wait. You can make the measurement by yourself on your side. My benchmark is more tuned for a small CPU like a laptop. So on a server one, maybe I need to stress a bit more the cache hierarchy to really see the measurement. But, you have the example on how to see it. But you see, the gap is a factor 5, 6. So if you are there instead of being there, you lose a lot of performance. For aliasing, so Intel is saying, yeah, we solved it and it's solved. Still there a bit. Not the factor 2 there was before, but still there. So I put some arrays. This is exactly what I'm saying. I'm making the computation. Here I'm printing the alignment of the addresses. ABC, I can show the code maybe. Loop. So the loop is only this, the loop. Simply this loop. This is what I'm measuring. In main, I allocated several arrays either by aligning them or by adding some soft shifting one array a bit. Okay. And I get as result this. For K-align, 1.3 cycles per element. Unaligned, 1.06. That's, I mean, the numbers are not very big, but that's quite something. If you multiply by the number of elements you have here 25% of performance, something like this, already. For a simple, I mean, a common example, some loops with A is equal AI plus BI minus 1. This is something you often do. We do this in Grayscott. We have this kind of stuff. So we are impacted a bit by that, possibly. If you have a lot of arrays, not. If you have a lot of arrays, of course, the other arrays will take some time while the ordering is blocked. So it tempers this problem. So the problem is there only hardly if you have just a few arrays doing that in the loop. And I think I have a last example, which is the coloring issue. And the coloring issue, I said it has disappeared, but not for the L1 and the L2. So I can try to reproduce it for the L1 and the L2 with a small benchmark. So what is this benchmark is doing? It's just where it is. No, I'm on the old one. I have a loop here, which is using a certain number of arrays, as many as I want. So I can increase the number of arrays I'm using. Where is the benchmark here? I forget what I did. So you see I'm allocating, so either some blocks aligned or either some blocks unaligned, which means that I add some kind of shift after that to shift a bit the array with some non-multiple to be sure that I'm not multiple of some sizes. And where is the call? Here. I'm calling the loop either with the aligned arrays or either with the unaligned arrays. The only thing I'm changing is the address, the virtual address of the arrays. And I can run the program. And you have the time depending on the number of variables you have in your array. How many arrays I'm looping over. So you see that 2 arrays, well, 2 arrays, this is quite small, so you don't see anything. Here you have the cost. 3 arrays, we start to be a bit efficient. But then 20 arrays, I'm paying a price. I was at with 8 arrays. I was 8 arrays, which is what is efficient on the CPU because I have probably 12 an associativity of 12. So I should be efficient up to here with my CPU. And I am because I had at 0 free something. As soon as I pass the limit, we start to see that the time is increasing. So also this is an optimization. In your kernel, either you don't align the arrays, either you forbid yourself to use too many arrays in the same kernel. And sometimes in physics, I see a lot some kernels with I don't know how many variables, how many arrays which are summed, divide, blah 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 blah. And you have I don't know 20 arrays in the loop. Bad idea. Split the loop in 2 loops with 8 arrays on each side, and you get a better performance. Or shift a bit the arrays in that case, because by default malloc has made the mistake. And here I lose a factor 2 of performance, just because I'm looping. Just to say that the benchmark is looping with the same amount of size. And when I have more arrays, I loop on smaller. Okay, so I kept the same amount of data which is accessed here. I'm just changing the number of arrays I'm using to access it. So in a complex computation, try to split the kernel in a smaller one. This is far more efficient. If you have more than 8, 12 arrays, this is the top you should have in your loop. Okay? Maybe we should stop here because we are out of time. Questions online? No reserve for the vector. Yeah, I did not make a reserve for the vector, so no. But yeah, we should. But what I wanted to measure is not too much the time to fill, but the time to access. So this is not a problem. The forecasting output is showing data processed per cycle or time per cycle. Cycle per element. You have seen a lot during all my presentations. I like a lot to measure in cycles per element. Because if I know that the cache is running at 1-2 cycles per element for the L1, and I'm at 10, I know that I'm not in the L1 cache. If I'm computing at 1 cycle per element, I'm probably in the L1 cache. So measuring in cycles per element gives you some hints on where you are about the architecture you have underwood. So this is a metric I like to use a lot myself. Any questions? End of the week. End of the CPU week. No more me speaking about memory. You will be you will be sad. Or not.
Okay, thank you everyone for following this week. So many thanks also to all the satellite side, to everyone online, and also to the sponsors. So yeah, that's the end of the CPU week, and we will have the pleasure to meet you again next Monday for the beginning of the Eve lecture on the morning and the beginning of the GPU weeks on the afternoon. And you will still have a surprise for tomorrow, but only you in Annecy, and will not spoil anything, but normally you will like it. And that being said, have a nice weekend, and see you next Monday. Bye.